Good morning, ladies and gentlemen. I have the pleasure to welcome you at GSI. GSI is a Helmholtz Center for Heavy Iron Research, and most of you have probably never been here, and for you I have prepared a short presentation on what GSI is, what FAIR is, what Helmholtz is. My name is Peter Spiller. I'm heading the sub-project CIS 100, CIS 18. Germans like long names. CIS is the German name for Schwerionensynchrotron, which means heavy ion synchrotron. These are the big circular accelerator in the north of our accelerator facility. And the 18 stands for the magnetic rigidity, and the 100 is also the magnetic rigidity of the big new machine that we are presently going to build. And I will show you a little bit what GSI is, what FAIR is. I have not much time, so a brief presentation on the basic or fundamental things we are doing here. So this is a map of Germany, as you are almost in the middle. And the Helmholtz Association is the biggest research organization in Germany. So there is, as you can see on the left side, about 50,000 employees, about 6 billion euro annual budget, 18 large-scale research centers, and many, many international users. Of course, you don't build very expensive machines and facilities only for the few experimentalists you have in-house. Usually there's broad communities worldwide who are going to use your facility. This is also what, of course, basis is for building FAIR, our new big project in the east of GSI. It's an expensive, large-scale facility, and that's one of the missions of the Helmholtz Association, to build large-scale facilities or large-scale experiments, like polar ships, high-field magnet laboratory, big accelerators, fusion experiments, tokamak, stellarator, and things like that. So the organizations have different purposes. You see there's coastal research, polar research, climate research, aeronautics and space, plasma physics, fusion, of course, environment, materials, energy, cancer research. So all of these topics are addressed by the Helmholtz Association. We are at GSI. GSI is the part of the buildings which are completed here on the lower left side. You are exactly here. No, you are here, sorry. This is the new building that we are going to use for controlling our new accelerators in the east of GSI, the new control center building. And the upper part shows you the construction site. It's a little bit older picture of the FAIR project. So this is GSI, the Helmholtz Center for Heavy Iron Research. Exists since 1969, where it was founded. This is more or less a national facility. 80% of the budget or a bit more comes from the federal government and the state. Usually for the Helmholtz Center, the local state covers about 10% of the annual budget. We have two Helmholtz institutes in Mainz and Jena. These are towns in Germany we probably don't know. And yeah, we proposed a new project, a new facility. Actually, 2001 we wrote the conceptual design report, so this is already a 20-year-old story. And about 1,500 people who are working here at GSI. So we call ourselves universe in the laboratory. So we explore the universe in the lab. Actually, we are also ground lab of ESA, because we can generate with the heavy ion beams conditions which are relevant for radiobiology or for astronauts flying to the Mars, for instance. So the basic question, what are smallest building blocks in matter? How and where are they created? How are the chemical elements formed in stellar explosions? What does matter look like in most heavy objects in the universe, neutron stars, things like that. Yeah? The point is we can create these exotic states of matter in the lab here at GSI by using the heavy ion beam or the ion beam made from the accelerator facility. You see two colliding nuclei here. in a short moment in time, you generate exotic matter that you find elsewhere. It's very seldom on this planet, but in universe, exotic state of matter, extreme forces, for instance, at colliding neutron stars and things like that. So that's GSI, the facility which has been, which exists, which are running. There's a user program. Machines are booked out for several years in advance. Besides the big project, we have to deal with that as well. So we have to maintain the machine, we have to upgrade the machine, we have to run the machines for the users. Of course, the user time is a little bit reduced because we are all totally overloaded. We all work for the experiments which are conducted here at GSI, but we also in parallel realize the big machines in the East. So there's several ion sources. We have a broad flexibility in producing beams, different ion species, from protons to uranium. We can accelerate all ions. And for that, with different parameters in a time-sharing mode, we run up to 6 experiments in parallel in a time-sharing mode, serving with usually 3 different ion species, making beams of different ion species. For the experiments, and the first stage in acceleration is a linear accelerator. UNILAC is a universal linear accelerator. It's a very old machine, but still the most powerful heavy ion LINAC worldwide. And this machine serves experiments in this first experimental hall, which was built in the 17th. There's nuclear physics experiments possible since 20% of speed of light is already achieved. And then you accelerate further in the ring accelerator, this 18, up to 90% of speed of light, depending on the ion species, of course. Then we have some sophisticated experiments, which are also basically accelerator sections, the called fragment separator, where we can separate nuclear fragments in a kind of mass spectrometer and inject these rare isotope beams into storage rings, or transport the primary beam or secondary beam to experimental areas. And we have a smaller ring, new storage ring called cryring. This is a facility that runs and where we do experiments. This is how it looks like. This is an old picture of the UNILAC. The circular accelerator looks a little bit different, of course. So these are quite big machines, a lot of technology, and GSI is doing experiments since decades. So we have well-organized way how to select proposals for using the machines for the experiments and plan the beam times. So that is, I always tell my boss is the managing director, don't tell the politicians only about exotic particles which they don't understand at all. So they would tell you this is no meaning for society. They may say that sounds interesting, but what it is good for we give you billions of euro. So we do a lot of technology development here. We have actually a technology transfer department here. And there's, of course, lots of opportunities for applications. We have a superconducting magnet department. We are developing fast-jump superconducting magnets, and now we say we build an AC energy cable, superconducting energy cable, for instance. We are able to find faults in superconducting busbar systems with a precision of sub-millimeter, and now we say we save critical infrastructure. We apply this technology to undersea, underground or underwater cable in the sea lying between, let's say, Sweden and Germany, and we can detect the fault in 200 kilometer difference with a precision of a centimeter. This presently we show the companies that we are able to doing that. So there is a lot of applications possible. Of course, usually scientists don't think in applications. They are, I mean, you know this. They work in their own universe up to 12 o'clock midnight, and usually you have to tell them, please look also for applications, and there's lots of applications, and this is what, of course, politicians like. One of the applications we have developed a cancer therapy. Here at GSI, built a pilot facility and treated about 400 people here with heavy ion beams. And since this has severe or significant advantages compared to the standard radiotherapy you get in a standard hospital in terms of precision in the spatial distribution of the dose that you deposit in the cancer or in the tissue. This is a success story. In Heidelberg, we have built a small accelerator for the clinic, and they treat about 1,500 patients annually, and works perfect. And this is, of course, something where our funding agencies say, something relevant for the society. So GSI is still involved in improving this technology, for instance, improving the structure of the slowly extracted beam, or enabling further parallel operation, which increases the efficiency of using the facility in Heidelberg. This is one of our technology transfer stories. Yeah. We also discovered a number of new heavy elements, which you find probably in the school book meanwhile. And since we discovered them, we were allowed to give them names. One is called Darmstadtium for the town here nearby, or Hassium for the state of Hessen. So this is nuclear physics. And we, with the fragment separator, generate huge amount of nuclei far away from the line of stable elements, and discover the processes how, for instance, the heavy elements are generated in exploding star supernova or in normal solar life cycle. So the FAIR project is a unique facility because while others accelerate electron and proton beams, actually there's different communities in the accelerator field. Most of them build machines for proton electrons. Our focus is heavy ions, and there where I always say we have the best in making machines for heavy ions. For uranium beam, we have to be world leading, for instance. Yeah? So our machines are always optimized for heavy ions or for heavy fragments, which you produce within a collision with the target. So we form exotic nuclei, do basic research, and as I said, we don't build these machines, of course, only for the experimental groups we have at GSI. We have experimental departments here, but of course, usually in these different areas of science, there are international collaborations which are using the facilities. So this is 5 times larger. The red part is what we are going to build. You have the opportunity to visit the construction site. The SIS 100 is a machine which is about 1 kilometer in circumference. It's not the biggest machine, but this is a machine which is unique in terms of acceleration of highest intensity of heavy ion beams. This is a special design. We have invented new technologies, new lattice structures in order to be able to generate beams with the highest intensity of heavy ions. Then we have the big brother, so to say, from the fragment separator is our super fragment separator, then, which consists of a radiation hard magnet part and superconducting magnet part. And depending on the funding, of course, then we will further on extend the facility to collector and energy storage rings to be able to digest anti-proton beams that we are going to generate from the proton beam in an anti-proton production target. This is the next goal after we have completed, we call that modularized start version 0 to 3. This is up to here, comprising the NUSJA, nuclear physics, nuclear structure physics, and the compressed baryonic physics experiment, compressed baryonic matter experiment. This is what we can build with our present budget, but there is lots of opportunities here for further upgrade. So we are aiming for the highest intensities. Beam quality is always a topic which I cannot address in detail here, because concerns a lot, of course, on how much of the produced beam you can effectively use for your experiment, and this is our goal. So facility is part of the European research roadmap and priority in the nuclear physics community. So this is the biggest, let's say, project serving the nuclear physics community in Europe. The FAIR project was suggested by us, but GSI or Germany is now only one of 10 shareholders. This is an international project now, and there's contributions from all over the world. Actually, the biggest contribution originally was from Russia, and due to the Ukraine topic, several contracts have been terminated, and there's only one collaboration left. But there's many other contributions. Poland, big contribution, India, for instance, and this comes as in-kind contributions at most in terms of components. So we specify the components, and these countries basically develop and deliver the components for the machines and experiments. And communities we have already addressed. This is clear. There's the scientific collaborations, which consist of contributions or comprised of partners from many worldwide leading centers, of course. FAIR is huge, a big project, one of the biggest science projects in Europe. This is some impressive numbers. 2 million cubic meter of earth are moved, 600,000 cubic meter concrete are built. Actually, the shell construction is completed from the buildings, and a lot of steel for the reinforcement of the concrete is partly we have wall thickness of 6 meters with a lot of steel inside for shielding purposes. Because FAIR is situated in area which is partly then afterwards, after we have completed the facility, still public. So we are in the phase of procuring the accelerator components since several years. Actually, lots of components have been delivered. We have huge storage areas. One big storage area nearby is now full. We have had to rent a new storage area in order to digest all the deliveries. On the right side, you see some superconducting dipole magnets for this 100 or cavities or local cryogenic systems for distributing the helium over the facility. Yeah, and actually for the high energy storage ring, which unfortunately because of budget constraints we cannot realize presently, the money for the building is missing. The machine components are already delivered to a large extent. So this is, let's say, an internal management issue. But most of the accelerator components, or big fraction at least, is delivered, and we have started installation early this year. In January, we have brought the first machine components into the SIS-100 tunnel. So a lot of high tech. I mean, you know this story is clear. Superconducting magnets, cryogenics, extreme vacuum is required for the heavy ions, much more demanding than for the acceleration of protons or electron beams, because heavy ions usually have the tendency to change their charge state when they collide with residual gas atoms in the vacuum system. So there is a lot of high-tech development, and we have GSI have lots of technical departments who usually do a very good job here, and we have lots of collaborations, of course, helping us to develop this hardware for the machine. So that is a short introduction in where you are and what we are doing here. Accelerator lab, typical, and I'm not sure if you have ever been at an accelerator laboratory. You have a tour, I guess, also through the accelerator facility and through the buildings. As I said, shell construction is completed. The building infrastructure is being integrated. Cable planning, cable laying is a big issue. 7,000 kilometers of cable, big story, and you get an impression. And I wish you a successful workshop. Lots of new opportunities, of course. Hopefully also you can establish some new collaborations here. So welcome at GSI.
morning. That's the reason. I guess most people are still in either jet lag or maybe they trying to catch some extra hours while watching the YouTube broadcast of this event. So please, also like a warm welcome from the organizers, both to the people here, but also listening in from abroad. I just have a few organizational announcements just to sketch out a bit how this workshop is being planned out. And I hope this will answer some of your questions that you may already have. So first, welcome. This is the 7th installment of the European GNU Radio Days. This is the first time that is hosted outside of France, in Darmstadt, in the City of Science, and in the deep, dark woods. So this is also the area where the grim fairy tales are from. And we thank the previous organizers for the trust they put in us that we could host this over here, but also in your interest for coming here, because many of you had a long journey coming here, and it's well appreciated, and I hope we can make it worth your time coming here. The European GNU Radio Days is like the smaller sibling of the GRCon. It's basically the key event for the European software-defined radio community. And the special theme of this workshop is that we wanted to introduce GNU Radio 4.0, what's about, and you're fostering collaboration between academia, industry, and individuals alike. And what you already heard in the introduction by Dr. Spiller is that we're basically a research facility that provides a research platform with a set of accelerators, but also a petawatt laser and high-performance computing center, one of the top 200 green IT computing centers over here, which are all used by more than 3,000 scientists to do fundamental research from cancer research, applied science, but also fundamental science. What is the origin of matter? So we have a fully packed program. Basically in the morning, mostly keynotes and talks and lightning talks. Then a small lunch break, which is over in the cafeteria, which you're free to choose your own meal. And then in the afternoon, we're getting down to giving out the meat. We have a certain set of tutorials where we have this afternoon the first general introduction to ease people in. What is GNU Radio? Why GNU? Why radio? And then branching out in two different domains, because as any problem, you have always different views on the same project. So we split it up into users or non-developers, which Jean-Michel Fried is taking care of, which will be behind in the KBW, another lecturing hall, and then for developers. And this evening, a social dinner. So we're very lucky and fortunate that we could get 3 excellent keynote speakers for this workshop: Eric Blossom, Johann Meschendorf, and also Josh Morman, which basically start off the day. So, so please, if you can, maybe try to be maybe 5-10 minutes early, because they're great speakers. Then followed, we have like contributed talks by different partners from industry, academia, and then followed by lightning talks. And this is basically free for all. Some are already scheduled, but if you have any ideas or aspect that you want to convey to the community, you get 5 minutes. Think about like how can you convey your message within 5 minutes, and try to be, it can be spontaneous, can be stimulating, or also like entertainment. I mean, entertaining, you don't have to be serious about it. There's still a lot of slots open. If you have an idea, please approach us and give us the slide maybe a day before, so that we can prepare accordingly. So first of all, welcome. The first task you achieved already. You managed to come here. You found Darmstadt. Now, more precisely, you also managed to be here in the main lecturing hall. So you entered the main entrance here. The main lecturing hall is here. And the canteen is just opposite of this building, so that is easy. The user tutorials will be in our second lecturing hall, which is just down the road. There will be signs that you can follow and then enter. It's easy to find. And for the social event, one of them will be on the terrace just in front of the canteen. What I would ask you, because everything is green, but as you see, we have like a big construction site in front of us, but also a large part of the GSI and FAIR facilities are construction sites, but also industrial installations. So there is not free of all hazards, so there's some high voltages, high currents, and for for your own safety and so that you're not getting lost, because that's very easy, guides you around. That would much appreciated. So tomorrow, there's there will be like the photo event for the workshop, because the weather is nice, and we're gonna have this at the terrace, so just before lunch. So everybody who wants to be on the workshop image, just before you head on lunch, don't forget, just let's meet in front of the terrace over there. And then this is then followed by the laboratory tours. So yeah, big site in terms of our keynotes, talks, and tutorials. They're live streamed via YouTube, but we have also like colleagues and co-organizers that will take pictures, so you don't have to take pictures on yourself, but we will upload them to the conference webpage after being screened, because there's, maybe where's Waldo or where's Wally? We all love taking pictures, but not everybody wants to have taking a picture of themselves. So please respect intellectual property rights and the freedom of others. And yeah, we'll post those links and screen them just to make sure that they're appropriate. So yeah, workshop photo just before lunch tomorrow. Our tour guide and our master of the tours will be Dr. Jens Stadelmann, who's also sitting there at the table. Both tours start here, just in front of the lecturing hall, in front of here. And Jens and Shahab whipped up an interest in UNILAC, the linear accelerator, one of the big experimental storages ring, the medical cave, and some experimental stations. Both tours take about 1.5 hours, so be prepared, hydrate, and yeah, take your time. And also there's a small safety intro that you have to sign up, so please be on time, so that'd be appreciable for everybody. So now the question is, like, maybe you all got one of these cups, and you might have wondered, what is this? And some people might think like, oh nice, if you're an RF engineer, it's a Faraday cup. So if I have some RF equipment, I just put it on top of the chip, and it saves me from some radiation and electromagnetic interferences. Some people might think, like me, oh, I have a cup, I make a antenna out of it. I calculated, sorry, it's not possible because the diameter is a bit too wide and not long enough, but almost. Or you can connect a string with 2 cups with your best pal, and you have like a string phone, You're closer because GNU radio has been used for telecommunication, or there are 101 other possibilities what you can do with a cup. But I think the best purpose is, please use this cup as a discussion starter to share some ideas over coffee, tea, or other beverages here on site or when you get back. And yeah, let's help to grow the community, shape some collaborations, and help the GNU radio community grow, foster, and go into the next decade. So all are welcome for the social event. The other social event on Wednesday evening will be in a beer garden nearby. Here's like the Fair and Square hotel, and it's easily walkable. Takes about half an hour. And if you look into your badge, then you will see some vouchers for free drinks over there. Please, if you don't find them or you haven't checked in yet, please contact Maria. They also have the directions in case you're getting lost. And if you need any other assistance, or if it's a bit too much to walk, please let us know. We can also organize a shuttle. And just to give an impression on, yeah, it's a nice place. It's very green. You have like peacocks and other wild animals, and it's a good place to share a drink and some ideas. In terms of technology, as you may have seen, we have public Wi-Fi and also Ethernet on the table, so please feel free to approach, use the tables and sit there. You may have also seen we have like a color coding on the badges. If you have any questions, the ones with the blue are the co-organizers. They know what's going on, and they can help you directing or at least relaying the information if you may have some. If you're coming from research organizations, EduRoam is your friend, I think, but for all the others, we have also like a free GSI and FAIR guest Wi-Fi where you just have to acknowledge the terms and you get in, and the LAN over here if you need like larger downloads. All of our infrastructure, we are public infrastructure. Please use it responsibly, respect others' intellectual property rights, and ask you also to keep it professional. listening in over the internet. We have a metrics channel where we share information both during the talks, but also social, if you want to organize some meeting in the evening or some other things. So it's metrics, European GNU Radio Days 24. It's hosted on the GNU Radio org, also site. That's all from my side. And now I think it's my pleasure and my privilege to introduce Eric Blossom. I guess he doesn't need any introduction because we all know him. He's the entrepreneur and one of the fathers who invented and shaped the software-defined radio community and scene over the past 25 years. And we're very fortunate that he could come and share some of his experiences, how it's all started, what he learned, and what recommendations we could learn out of his experience to move forward to the next decades that are to come. So please give a warm welcome to Eric Blossom.
Thank you, Ralph. And then what do we got here? What am I, oh, this is my clicker? Okay. Sorry, I'm on, can you hear me? How's my sound? Okay, it's green. All right, I'm talking. It sounds like I'm, okay, yay, all right. Okay, first of all, let's see, I've got some slides here. Mostly I want to just start out by saying that probably the best use of me is not for me to like drone on for this like full time slot, and I would really like it to be interactive if we can. I understand there's some microphones around. There's apparently one here. Is there another one somewhere? And I am perfectly willing to be interrupted at any time today, including while I'm up here talking. Because if you've got a question, please let me know, and I may handle it in the moment, or I may say, okay, we're going to get that in just a second. Partly I'm trying to be as helpful as I can. Part of what I'm going to talk about is how GNU Radio got started, and there's a very relatively small number of people that were there at the beginning, and now there's more people. So I want to kind of make sure that we take a look at how it happened, partly because Ralph had asked me, he'd heard me do a similar talk a year ago, and he found it useful. And part of what I'm looking for is, what do I have that I could share that will help us continue GNU Radio for another 20 years, and how all about it, like the community, how do we build it, where do we go, how do we fund it? Do I have to point this in anywhere? It's on red. Is that to green? Okay. Okay, introduction. Okay, so what do you need to know about me? I think that's the thing is that I founded the GNU Radio project, and I'll talk about how that was, and that was in 2001. And then I worked on it as a full-time endeavor for about 9 years. And what else do you want to know about me? Most recently, my last sort of professional engagement was I was working at Planet Labs, which is like a new space company, and I was designing the high-speed radios that downlink the images. Planet was in the business of, in one sense, a data company or a platform company, and we had 150 small satellites in orbit that covered all the land and coastal areas of the Earth every day at about a 4-meter resolution. And then we had some other satellites that could do about 50-centimeter resolution. And now we have some in orbit right now that'll do about 30-centimeter resolution. So what's great about those is so basically I worked on a team that basically built those high-speed radios. So in the small satellite, which is literally like a 3U CubeSat, we were able to about 1.5 gigabits a second. And then by just continuing to tune over time, it's now running at about 1.9 gigabits a second, which is quite an accomplishment out of 2 watts in a little thing that's 3 liters big. And then we went on to build for the satellites that can do the 30-centimeter resolution. Plus, one we just launched about 2 weeks ago was a spacecraft that's called Tanager, And it has got a very fancy hyperspectral instrument in it that was designed by JPL. Got 450 bands. It was primarily designed, or let's say it was primarily funded by people who wanted to keep track of like methane emissions, from orbit. You can find leaky pipelines and ships and everything. But in fact, it's a completely general instrument. And, it's very, very snazzy-dazzy. It was just, again, launched a couple of weeks ago. Planet's been able to talk to it, but it'll be, probably a few months in commissioning because it's the first of its kind. Okay, that's about that. Just another kind of personal story that I told a few of you this morning is that when I first started as an undergraduate at university, I had come in and I'd discovered that there was this physics series that you had to go interview for. There was the regular physics, the physics for the non-science and engineering people, kind of like, physics with almost no math. And then there was the kind of normal physics with some calculus. And then there was this other one that was the intensive general physics series. And you had to go talk to some professors to get in it. So I ended up in that program, which turned out to be taught by 3 particle physicists. And there were 6 students. And what was revealed as we went on was that they were interested in how do you create physicists that were actually working. So it was taught with full rigor, looking at every case where what's the next exception you ran into historically, and then what was the solution for that. And I really enjoyed doing that. And in the summertime, I worked as a research technician building these multi-wire proportional chamber detectors that were headed for Brookhaven. So that was as an undergraduate doing that. And in one sense, it's really great fun to come full circle back around here. And here we are at this place dedicated to physics and all of the engineering and science that goes behind making it all happen. Great, thank you. Why this talk? I talked a little bit about this, but mostly because Ralph had asked me. I was coming, and then Ralph said, "Hey, will you talk?" And I said, "Sure." And then I don't know that there's anything else I want to say about it, except that we are really at a transition time right now with the introduction of the 4.0 release. This will only have been the 4th time we've made a really large change in the architecture of GNU Radio, in the way where it is changed. We're willing to make, quote, breaking changes, and we've only done that. This will be the 4th thing in 24 years. So I think this is, in one sense, one of those possibly, dangerous and exciting times for us all. And then I want to just set a bit of context for this next part, because all of a sudden the next slide you're going to go, what? So I want to just kind of set up that this was about 1993. And I had been working for a classic Silicon Valley startup. I was working 90 hours a week. It was a software startup. It was back in the day when there were all kinds of processors and all kinds of operating systems. It wasn't just that there's 3 kinds of processors and 3 kinds of things. There were all kinds of stuff going on. And my then, at the time, girlfriend was super happy. I was completely occupied because at 90 hours a week, how much trouble can you get in? And at some point, she was like, how would you come move into the wine country with me where she lived, right? And so she's says, come, it'll be great. You'll love it. You won't have to work 90 hours a week. And I said, okay, great, let's do that. And at the time, then I was thinking about, well, now what? Now that I'm released from, intense focus. And I was curious about really what was the nature of, what is the physiological basis of knowing? Where does knowing happen? Where does it happen in the body? But what I noticed is I also was unable to pronounce the words in the primary, the abstracts of the primary literature in neuroscience. I said, I should probably go back to school and take some organic chemistry, molecular biology. Ran into a really great professor who was his last year teaching, and he's like, oh yeah, you gotta learn virology, because that'll let you get past the brain, into the brain, and just super interesting. And I was about a year into that, and then this happened. So, 1993, the NSA introduces this thing called the Clipper chip. This was this idea that they were gonna build this thing, and it was specifically designed to secure data and voice. And it had this funny feature which was called, it talked a protocol that had this field in the protocol that was the law enforcement exploitation field. So basically, it arranged that in every conversation that you had, it made sure that the keys to the conversation were transmitted right up front so that authorized people could intercept your conversation. Now, this created quite a stir. It was really a time of really great concern in the U.S. in particular, and I think it was in other parts of the world also. And it was a question about, well, do I have the right to have a private conversation? I looked at it like, well, in the old days, if I wanted to have a private conversation, you and I would take a look around and we'd go for a walk in the woods. It was a completely natural thing to do. So anyway, this came out. And at the same time, AT&T introduces this as gadget. This is like a telephone encryptor thing. Does this thing point or no? Anyway, it went in the handset cord. This is like wired phones. Remember those back in the day? So it went in the handset cord between the things. So it would work with a PBX or your home phone. ISDN was not really a thing in America. It was a little bit later, kind of an interim technology. Mostly people use it for access to the internet. And so there was all kinds of conversation around this. And this is a model, this 3600E, that featured that Wi-Fi. Ah, great. Okay, yeah. So anyway, handset cord, goes in there to the phone. And then what it turned out was that a year before, they had built the same model that didn't have the Clipper chip in it and just had the data encryption standard, the 56-bit key. And it turns out that the order that things happened was the place with the version with the 56-bit DES encryption came out, and then apparently AT&T went, or NSA went, woo, and so they, in a big hurry, built that Clipper chip thing. And then they recalled all of the previous versions of these, and then they introduced this one. So I looked at that and kind of like, well, how hard could it be to build one that doesn't have that flaw? So, I mean, you look at what's inside of this, communication privacy device, and there's like a modem in there because it talks over the phone line. And there's some kind of crypto of some kind, and there's a vocoder in there. And being a perpetual optimist, I'm really in the, well, really, like how hard could it be? I'm a background in, I knew something about, DSP, but, so anyway, I headed out to go figure out how to build one of these things. And then I was looking for, well, who else might be interested in this topic? And that took me to this group of people, which were like the cypherpunks. And so this picture was from Wired Magazine's cover for their second edition ever. This guy here is Tim May. He's a physicist from Intel. And basically, he was famous at Intel for solving this problem with alpha particles that were causing bit errors in their DRAM. And what he figured out was that they were in ceramic packages. Your ceramic package is slightly radioactive and it is corrupting your DRAM. So they figured out how they go plastic packages and more charge in the cells. He went on and won some IEEE award for that work because it was really kind of a mystery at the time. This guy's Eric Hughes. He was a mathematician. And then this is John Gilmore. And Gilmore, I'll talk about in a little more detail because he actually feeds in directly into the origins of GNU Radio. So this is Gilmore. I met him at these meetings. And part of the thing was Gilmore, to a little of the background, I mean, you can read it, but basically he was employee number 5 at Sun Microsystems. Then he founded a thing called Cygnus Solutions. And Cygnus Solutions was in the business of supporting like the free software tool, like the GCC, the tool chains. And how they made their money was at the time, again, this is an era when there's more than 3 kinds of processors. So a lot of embedded processors were coming out, and the people that were trying to sell those or build things needed tool chains, and they also wanted them early. With the simulators, for example, if you've got some new game machine of some kind, and you're not sure when it goes, you really want your software developers to get going as quickly as possible. So anyway, Gilmore was part of the crew that did that at Cygnus. And we met, these meetings were happening at Cygnus, which was in Mountain View, California at the time. And there's just a really interesting group of people, and I'll just talk about that. And there's lots of things came out of that group, including some things like BitTorrent came out of there. Bram Cohen would like not shut up. He was always talking about this, always talking about this, always talking about this thing, and people are like, and finally, like, oh my God, it's the vast majority of the data transfer on the internet. And then John also is the founder of the Electronic Frontier Foundation, which for those of you who may not know, it's a kind of like a civil liberties group really for the online universe. And they've grown from a small place where there was 3 founders to the place that's huge right now. They do all kinds of interesting things. All right. So I learned some things, a bunch of stuff building the wired telephone encryptors. And the first thing I want to point out is that I did them wired because it was really the only option at the time. There were cell phones, but there was no smartphones. So the choice is like, okay, how can I get any software into these things? There's really no really easy way to do it. So we started out with, what can you do? I can do wired. And in my case, I did starting with what we would call in the US as POTS, plain old telephone service. That's the 4 wires coming out of your wall. And I plugged it in, and I had met, one of the people that I met was Whit Diffie. And Diffie and Hellman were the inventors of public key cryptography, at least in the open. And Whit, his motivation for inventing that is he didn't want to have to trust anybody, including his IT people. So how do you build this thing out so that that was what was his kind of driving his interest in all this. So he basically became a mentor to me, and so I learned a lot, and a customer. So he was at Sun Microsystems at the time. He was originally a fellow at Sun Labs, then he ended up at the chief security officer. Again, just more interesting people. The point being, I built 2 generations of these. Even though I had customers at the very beginning, what it turns out is that I probably had the only customers. And it turns out that it was really kind of one of those ideas where I wanted these things to exist. I wanted to be able to have a private conversation anywhere in the world. But for the most part, people do not care. And I would say, meanwhile, 20 some odd years, almost 30 years later, it's pretty much the same situation. There were some European colleagues of mine that started the GSMK, the crypto phone. There's kind of the same situation. They might still be around. It's kind of like effectively a zombie kind of a business. It never really took off. But I learned a lot and met interesting people. Not the least of which was the classic. Everybody learns this is just because I want it doesn't mean it's a good business idea. But when you started looking at what's in there, towards the end of this run, because what I really wanted was the ability to have this gadget in my pocket that I could talk on. And I was looking at reading the standards for the US digital cellular standards. We did eventually get the GSM, but before we got there, we had these 2. And the IS-136 was partly ran on the same band plan as our original analog stuff. And what was interesting about this standard is that it had, if you're building a cryptographic system, generally the idea is you take your data and you compress all the redundancy down with it, like compression, and then you apply your cryptographic algorithm on top of that. For some particular reason, it was backwards on this thing, which is like the forward error correction was on the wrong side of the crypto. And it was like, oh, wow, how did that happen? Okay, and then we're like, And then on IS-95, this was a CDMA1 system. It had, again, this is like, you could just read the specs, and if you got some clues, you can figure this stuff out. So it had what it was effectively linear crypto. That was not actually crypto at all. There were 42 equations and 42 unknowns in Z sub 2. So there's like 42 bits you got to find, which seems kind of large, except it's linear. And it was helped out in this, there's a variable rate vocoder. So you're either talking at full speed and it's using, like 8 times as much data, or you're at half speed or a quarter speed or an eighth speed. And of course, at 8th speed, it's like just a few bits being transmitted. However, it's got discontinuous transmission, which means that every time you stop talking or pause, pretty much the last thing you say is nothing, right? And then the thing shuts off. So you effectively have you have this known plain text. So you can just get, within about an eighth of a second, you can solve for this thing. And there was a paper published about the attack. I didn't make it up, but it was, I'm sorry, I looked for it. I couldn't, in 5 minutes, I couldn't find it. But I was like, wow, that's interesting. And I just kind of wondered, because here I am, I'm really kind of pretty much given up on trying to do anything about building gadgets in this area. But I was like interested in this. So my question was then like, well, I want to pull the bits out of the air just kind of to make a point about it, right? Well, and I could have been like a regular sane person and just gone and rented a piece of test equipment and just hooked it up, you know, go pull the bits out and be done with it. But I was thinking, well, what's the fun in that? You know, so why don't we try, you know, what now? So as I'm unwinding from that and I'm looking and I'm like thinking, wow, here's my next idea. I'll teach myself digital comms. This is a thing I don't know, looks really interesting. And my wife is she's been super supportive our whole time together. We're about like 30 some odd years together. And she was like, that's really great. I'm all for supporting that, but please, I don't want to be poor while you're doing that. And I'm like, okay, I hear you. Good. And I started looking for, well, what do I need? I need like a development platform. I want to go out and buy something where I can start to teach myself this stuff. So I look around and I'm like snooping around on the internet and I find this basically eval board that's from this Canadian company. And it had like an RF front end on it and an FPGA and a DSP and some other kind of processor. And it was like, wow, it has like everything. And it was about $10,000 US. And that was kind of in the realm of my personal, I would spend that much money to get a new thing I'm going to go teach myself something on. And then I go look for like the software licenses it was going to take to turn all this on. And that was like $70,000 worth of software licenses. And I was like, whoa, not doing that. So I was kind of like, So then, meanwhile, you know, life goes on. I'm kind of looking around, but I'm like, okay, I'm still interested in this. And then I've been in contact with Gilmore, because he and I have been in contact for over the years. This is, meanwhile, like 7 years from when I first met him. But we kind of talk every now and then, a couple times a year at least. So I'm like, go up to San Francisco. We have a nice dinner at this Thai restaurant. We're just sharing about what's going on. I said, hey, you know, I'm looking at trying to teach myself digital comms. There was this standards are kind of messed up. And but I said that this license, it took like $70,000 worth of licenses. Then he goes, Gilmore, again, having made money, you know, building and free software, a license under the GPL, says, well, let's start a free software project. And he said, and I said, okay, great. And he says, well, make me a proposal for funding. And I was like, okay. So, you know, I talked to him like one more time. And what's good about, the thing I want to keep pointing to is about relationship through all of this. And I think it's how the whole world works, but in particular, here's another example. Gilmore had been a customer. He knew me. He knew what I was capable of. And he was like, okay, I will fund this thing. We found a donor-directed charity, and he basically agreed to fund the development of what became GNU Radio. And part of my very favorite part of it was that it was really easy. It was some of my favorite time to do work, partly because the arrangement with John is like one phone call a month kept the money coming. And I was getting paid a reasonable rate. And I didn't have to keep track of any hours or things. Just go do work on the thing and, you know, keep me posted. So that's how it started. And then we returned to the question, okay, well, where do we start? Now we're back to where do we start again? And on this time, it's like, so I start with, I graduated with a degree in electrical engineering, but I was really mostly kind of on the computer science side. I'd kind of gone to the dark side from the physicist point of view, because they were like, don't get sucked into those things. They're really interesting, you know? And I was like, sorry, I did, you know? And so, but I built a kit. Could have done some amateur radio thing, but this was like a company like Ramsey Electronics. It had like 14 transistors in it. So the point being, there's no magic in there. It was all like on this board, and then you get to learn how to probe, RF and not disturb the signal while you're poking at it, right? Kind of useful. I figured before I try to build one that's like almost completely abstract and out of software, I probably ought to know how to build a piece of classic hardware. And we started out then to look for, well, what's the starting point? Somebody else must have looked at this. There was some earlier There was a military project called Speakeasy that Joe Mottola had done. There were some papers published about it, not really directly applicable to what we were interested in. But then I was snooping around, and I came across the MIT Spectrumware project. These guys, this was a pretty interesting thing. These two URLs, they're captures of different times. The thing is effectively, there's a lot of dead links back in here, but they published 14 papers that are really quite irrelevant. They discovered a bunch of stuff that was useful about ways you would do computation if you were going to do it on a general purpose processor, as opposed to it was all like one DSP. It was always like one sample in, one sample latency all the way through the things. And they also figured out some algorithms that were handy to do on general purpose processors. And there's a whole crew of people, including Vanu Bose and some other people. Tenenhouse is one of the professors. He had then gone to Intel, and I went and tracked him down just to go visit and say, hey, tell me, how did it go? You know, anything, I'm looking at doing something like this, anything you can share with me. And he was, as helpful as he could be. Anyway, they had a code base, and it was a reasonable place to start. I think about 5 or 6 people received PhDs working on this project, and it was around this particular code base that they were using. And that's where it originally came from. That's dead. I don't have the whole code base anymore for this. pSpectra is what it was called. It was in C++. I have no idea what the P of pSpectra was for. And then along with that, they had the same problem everybody has when they get here. It's like, I want to do a software-defined radio. I somehow need a way to get from the antenna into the computer. So at a simplest case, you need some kind of way to get high-speed A to Ds and D to As connected into your computer. Now, at this time, the fastest things we had going that was affordable was PCI, not PCI Express. So this is like the PCs of this time. They built this board they called Guppy, which was basically as simple as you could get, and it just had some, SMA connectors on the end, and then you plugged in whatever you wanted. Ralph, I know you had asked at one point, or I saw it in the comment in the code about where did this double buffering idea with the memory double mapping the same physical memory into 2 places in the virtual address space. It came in the Guppy driver. Spectrumware itself didn't do it. They had one paper, but it didn't really talk too much about it. But I looked at the driver to see how it worked, and I go, wow, that is super clever. So there was a trick used in GNU radio now, since the beginning of time, where to avoid having to manually manage a for loop, if you're like computing like some FIR filter, and you want to not have to figure out, am I at the end where I now need to wrap? So what you can do with pretty much all contemporary machines, the machines that it doesn't work on are ones which have virtual mapped caches, which don't exist anymore. The HPPA was an example of that. But you can do this trick where you have a piece of virtual memory, and then by using the right operating system calls, you can basically get it to map that same physical memory into the adjacent piece of the virtual address. So basically you have this sequence of data, and then it repeats right here. So what happens is you can just compute straight across that boundary, and your software doesn't have to know there's a boundary there. It turns out to be super handy. Anyway, that's where it came from. That's where the idea came from. All right, and then this was the very beginning. So we started with a pSpectra, and I was going to start to clean it up. And the very first thing, this is the first commit. It was 2001. And the first thing happens is there's a return value off by a factor of 2, and there's a stir length related buffer overrun. So this is how we get started with pSpectra, which I would, with no offense to any former or current graduate students, I would call, grad student wear. Like it got the job done for what it was supposed to do. Yay, we learned, we got our degrees, we went on. And they left it for other people like, me to come across. So we started with that and then went to town. Okay, Moore's Law, of course, obligatory. This is mostly why this is in here is just to set the stage for what what's the resource availability at this time? So let's assume it's like 2000, it was like 2001, and that puts us, here, and then like to say to 2010. And this thing is, we are in a really great time. This is the Moore's Law straight transistor count area here, all right? And then it kind of flattens out up in here. But what also was happening in this period of time, as the clock rates were just getting faster at the same rate. You did not have to do anything but wait, and everything ran faster, which was really good news, because if you think about it, we were trying to do these computations on this general purpose processor, and if you get the data rate up high enough, you cannot compute it in real time. So, but part of it is we could see that, this trend is really working for me over here. I could build it, I can test it, I can run it. In some places, like I can capture signals that I can go in on demod or whatever, but I can't do it in real time today, but I can do it in real time in 2 years. It was a very interesting time. And then part of what you see where it flattens out, all of a sudden you start having, here's 8-core systems, 12-core systems, 61-core systems, and we're now back into this realm that we have now, which is they're not getting any faster. The Dennard scaling has flattened out also. We've got it, we're power limited. The only hope at this point architecturally is more processing. And then, of course, the things that people are doing now is other architectures for computing. So there's the whole GPU thing, and making all this heyday in AI, but it really isn't the right architecture for computing those things. It just happened to be the one that was at hand. And there are other people who have designed like graph processing machines. A guy that used to work at Intel and at AMD as a CPU architect. I saw him do a talk on this. Here's how it would go if you were actually you're trying to take that graph and run it. This is what the hardware you would build. So, anywho, that's kind of the environment that we have, and we're again stuck out here in a place where we're being forced into heterogeneous systems. We've always pretty much needed some kind of FPGA or something for the very bottom of it, and I know that pretty much, so I was talking to a gentleman back here about trying to do the RF, the high performance RF at the very bottom is like for my control system, it's got some exact sample by sample and it's an FPGA, and those things are a pain to program. So, all right, and I wanted to start at Matt Edis, who recently, a couple weeks ago, was elevated to IEEE Fellow for his work supporting software-defined radio, which is pretty exciting. Matt was started at the very beginning of GNU Radio, and because one of the things we looked at was, hey, what hardware are we going to run this on? And we found some things which I'll talk about that let us get started initially, but like just the data acquisition board was costing more than the computer that we were going to run it on. So anyway, Matt and I, we met. We started. He had a job designing like Bluetooth ASICs that were used for some things. So he had a background in signal processing, and my background was kind of like generally like software. Yeah, I can do that, and I'm curious. So those are the things I got going for me. Anyway, he and I used to get together on the weekends and go, okay, I'll come to your house, and we'll work in your home office, and then eventually he gets a bigger office and so on, and like that. The initial hardware we used, again, we had the same problem with the MIT people. Somehow I got to get samples into my computer. And again, I had one Guppy board. They sent me one. I sent them. It was funny. I was looking, and it had, do not dispose of this box. It was one of those nice kind of folded cardboard with the foam on the inside, and it says, don't dispose of this box, reuse it. And I realized it's still, meanwhile, like 25 years later, it's still in my line of sight when I'm in my garage. It's got something else in it than the Guppy board, but it's like still there. Hang on, go in the right direction. Matt, okay. And this 4020 board, we ran it at 20 megasamples single channel because that was all it could do 4 channels, but it couldn't do them at 20 megasamples. And that was a straight just bandwidth limitation of the PCI bus. And then, again, it was just expensive. The thing was like at least 50% more than the cost of the PC we were running it on. And then we had the question, well, what's our RF front end? And it turns out we found these cable modem tuner eval boxes. So if you looked inside your cable modem, there's a little metal can in there that had, at least in the US, it has like an F connector on one side. And something out the other side. So we found those. That was reasonable for us. We originally used some US-based ones that were set up for, we had 6 megahertz channel spacing, and later we switched to European ones, which had an 8 megahertz spacing. And that got us to go, but again, this thing was not cheap. There were also, when we were looking at hardware, we looked at some, well, if you really wanted to spend some money, there were lots of people that would sell you fancier hardware. But it was like in the 20 to 50 grand kind of a category. So that was not, we started the thinking about what do we want? What would we want if we could have anything we wanted? What would the interface be? And that was a conversation that evolved over time. That was happening at the same time that I was mostly working on the software, but working with Matt on the development of what became the USERPs. And then when we started out, well, what are we going to build? What's the first thing after you what's the hello world of software-defined radio? Well, we thought, let's do like broadcast broadcast FM. This is your regular wideband FM, and you get in the car, right? Before there was digital sideband on it. And it exercises a fair amount of things because we were going to bring in either almost the entire band with the other thing, we can't get the entire band, but we could get like half of the FM band. And then you have this question of like, well, how do I do my channel selection and decimation and how I do that efficiently in software? There's the FMD mod itself, the signal processing involved in that. And then there's like audio output, which you've got, oh, your PC does audio output, no big deal. But then you run into this problem, which is, I would call it the 2 o'clock problem. And this is still not solved generally. And I don't think it's currently solved in the code base generally. And it's a real, it's the kind of thing you want solved. And this 2 o'clock problem is, I got a clock that's my A to D converters and D to A's are running on, which is almost certainly not shared with the same clock that's running my audio in and output, the A to D's and D to A's on this. You find the problem in other domains also. Anytime you have 2 different radio systems, and there's sample rates are different between them, or one is remote, one is in orbit, and one is on the ground, and there's a bunch of Doppler happening also. And what you also want is you want really low latency. So you really want the system to basically make, fudge it on a per sample basis. Like on the audio, you can get away with, if you're careful, you can either insert or delete one sample and keep the timing continuing to match, even though it's off by a part in 1,000 or something like that. If you don't, what happens is you end up with a thing that just gets a larger and larger and larger delay in it, which is terrible. Or the other case, and then you underrun because you're not keeping up. So again, this is something with the GNU Radio 4.0 scheduler, real time, yay, we should make sure that we've got a story that's about solving this problem. Okay, we got that working, no problem. Then what happened is we need the next more complicated thing, and in the US, we're always got some funny standards. I look at the European standards for digital, terrestrial digital television. Wow, it really makes great sense. We had this thing called the Advanced Television something, ATSC. And it's a reasonably complicated waveform, which means it kind of has one of everything with regard to signal processing. It has a block-based forward error correction in it. It has a convolutional error correction in it. And it has, kind of a bunch of things. So it was a really good thing to try to build. And there was no way at the time we were writing it that we could run it in real time. But they didn't stop us from being able to collect samples in real time. And I remember my office in Monterey, I got a big outdoor antenna and had it in my office and pointed towards the first television station that was broadcasting in my neighborhood. And we could just collect samples and then go grind on them. And then while we were doing this, and Gilmore had suggested this, he's, again, with his EFF hat on, because there was a group called the Motion Picture MPAA, Motion Picture blah, 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 something, who are the people that were they were the kind of people that were trying to make sure your set-top box couldn't play anything back initially. And then they wanted on this, they really wanted to, without going too deep into it, the television stations in the US do not pay for bandwidth. They were grandfathered in. So they might pay some kind of fee, but the fee is on the order of like, a few $100s, as opposed to the cellular carriers who have to pay billions of dollars for access to spectrum. So there's that as the background. And then the Motion Picture Association of America and their Copy Protection Technology Working Group made this proposal that they were going to use this thing and transmit this new digital signal, and they wanted to make sure, they wanted a bit in the data stream that said, "Thou shalt not copy." And we were like, "Oh, okay, really?" And they were sure that if they didn't implement this bit, that people would be dying, industry would, it would all be terrible. It would be terrible, terrible, terrible. So what they had proposed for us to do is build this ATSC thing. I said, yeah, we'll put the code in there that says if, the broadcast flag, which is one flag set in the header, is there, then we won't copy. But we also made the point that this is free software, and the very first thing anybody's going to do is just like if 0 and remove that one line that checks this bit. We also had prior art and court rulings that were related to crypto, where it was basically ruled that in the US, that source code is protected under the First Amendment. It is an expression that is protected, and so we have this open source thing that this battle got fought kind of in the crypto area, and then we're like, oh, we'll apply it here. We've developed this, software gadget that will receive this thing, and then I can even put the flag in there to check the flag. Then don't save it to the disk. Anyhow, we built that. Went to this big, conference down in Los Angeles, where the big Hollywood producers were there, and there was like, okay, here's their head technology guy, head lawyer, and then here's like the different people building consumer electronics, and they're all doing their thing. So we go, and I go under the EFF lawyers, and we just tell them what we're going to do. We're going to build this thing, and we'll say, okay, we could put the bid in. People will take it right out. It turned out that argument wasn't enough to get it killed, but that the EFF went on and killed it with the American Library Association, basically challenged it a different way, and so that bit never got deployed, so people are free to, look at the bits on the air and do whatever they want with them. Anywho, I guess what I want to say about this is I noticed that having this as a target to build, which was a fairly sophisticated waveform, was super useful to give something like, it's your use case. And we built the transmitter and the receiver kind of from the bottom up, the outer edge first, that you could connect together, and then built up both sides, the transmitter and the receiver, in parallel. Super handy. So I would think whatever we're looking for with GNU Radio 4.0 cases, on the radio side, we should pick some interesting things we want to do. And I know that some of us have already had conversations about this, but let's make sure we're building something that's interesting and hopefully useful for somebody, or lots of somebodies. GNU Radio 0.9 was the very first. This is a little bit scattershot on ordering here, but there's a whole bunch of stuff going on in parallel. This was the very first public release. This was at the end of, I started with the P-Spectra code, and by the time we got done, like bug fixing and restructuring and modern build system and all that, we ended up with about roughly like 30% was P-Spectra code and 70% was new code. And the total time, and in the meanwhile, we'd done drivers for those boards, and there's a bunch of work getting done. And it ended up being about 2 years to get this all done. And at that point, we were saying, that's the end of that line of development. We'd learned a lot. There was not a real future for us. I could see at that point that there was better options from like a software architecture. And so we parked this, and that was, that's what happened to that. Again, this is all kind of happening in parallel. So back to the question of, well, we've been buying these measurement computing boards, but they're very expensive and they require a desktop kind of a thing. And I'm pretty sure that Matt and I were having some conversation around this starting around in 2000. And I saw that the first commit I did on the software for the firmware was in 2003 in July. But I'm I do remember we were just trying to start with like kind of what do we want? What do we want the price to be? We talked to some folks that were doing that had built stuff, and they suggested USB, and there was USB 2 at that era, and they were already mentioning there was USB 3. Now you think like USB 3 is like 15 years down the road from when we were having this conversation. But anyway, we talked to people that it was kind of like, okay, well, it'll be USB. There was a part that, it was the FX2. The FX2 was like had a parallel interface on one side and talked USB on the other side. And that was this whole idea was what started with the usurps. And we used the cable tuner, the same RF front end we had before, which was this eval board for these cable modems. All right, any questions so far about anything? Okay, I'm going to talk in a little bit about kind of some funding things, like how do we get paid? I mean, I worked, like it turns out, I worked like 2 years on the first thing, and then this thing took another 7 months. This was the next version of Accelerator. There was no 1.0, there was just 0.9, and then we started to yeah, you're welcome. I haven't seen there's any shortage of integers, so I think we were okay. It was just like, it was never going to get to 1. So we started off, so the 2, and there was no, don't ask me, there was no 2.1 or there was 2.2. This was one which is really a rewrite. So we reused, the algorithms were reused with regard to the signal processing blocks. But I had learned a whole bunch from trying to working my way through the P-Spectra code, and we saw that there was looked like a better future to build out. So this includes really the kind of stuff that we still have in there, the streaming part. This was the idea that you had the buffering where you had the single writer, multi-reader things, and the flow graph, and all this whole business was in there. And it all had the Python bindings in there. And in fact, in the 2.2 series, the 2.0 series, the high-level manipulation of the flow graph was in Python, because it never was critical performance. Once you got that graph described, we would just flatten it all out, and then you handed it to the C++ code, which I thought was like really great. And then we had some customers that wanted to be able to deploy with no Python. So that got addressed later, but we live and learn. So anyway, and I also just like to say this is one of those ones where I was fortunate enough to have funding of being the people that like trusted me, and to say, you want to do what? You want to start over? And yeah, I do, because it's going to be better in the future. And we got it done in much less time, and it was the right call. We really had something that has now been carried on for 23 years. Not that it hasn't been improved along the way, but this fundamental architecture on the streaming side is the same core principles. All right, now into funding. So this is related into some conversations that people have asked. Ralph and I had conversations around this, just about like, well, how do you grow a project and have it go for 20 some odd years? And there are a lot of, there's a whole lot of, software projects that get started, and they go for a little while and then they die. There's a relatively small handful of them that really, I don't know what the percentages is, but it's like low. So you get something that it can go 20 years. But I know that part of it is there's people getting paid to work on it. They're getting paid one way or another. I was fortunate enough that I was just working on this full-time on the core and the design of it. There were other people that were working either for some company or enterprise or whatever that was related. So there was again, people that were either part-time or full-time that were working on it. And letting us, evolving it and letting us know what happened. So there's this idea that it's all free. I mean, no, because you can't get good talent to really work for free for a long time. You can get free talent to work for, for maybe a couple of weeks because it's cool. But if you want it really full time, you need funding. So I was fortunate enough that I had Gilmore fund the original development, which ended up being roughly, I don't know, a couple of years. And then he had introduced me to Jay LaPro, who's a professor at the University of Utah, who was running this place called, he was the head of the Flux Computing Operating System Research Group. And they although Jay had died in 2008, his group carries on, and they have this big test bed called Emulab. that is available to pretty much any academic kind of person. And it was designed for, it was early cases of software configurable networking and delay and all this whole thing, and it was a big, expensive thing. And Jay was like interested in the thing we were doing, and his whole group were kind of, in one sense, the masters of writing grants, because they'd been doing it for years and years, and they had a machine in place to do this. And he was like, great, yeah. Well, you guys write your part, and we'll get it all worked in there. And he was, when we first got funded, he was like, wow, this is the first time we've ever been funded for for a proposal that was pretty much just all bullet points. And we were like, oh, it worked. So anyway, that was the first experience for me of National Science Foundation funding. And it basically funded Matt and I to work on another couple of years worth of things. So part of the early development of the USERP was covered by this. And what the National Science Foundation really wanted for it, what the thing that was about, was their customer are academics, right? So these are lots of students. We wanted to basically serve as people that were wanting to learn about digital comms and build stuff. Because although, hey, MATLAB is super popular, but do you ever have heard of anybody that actually deployed a radio built in MATLAB? So there's this whole question about, there was a famous paper by Fred Harris that starts with, let's assume the system is synchronized, right, which is the hardest part of the whole problem that mostly gets punted, and your MATLAB workbooks don't have the solution to that in there. So anywho, there's National Science Foundation, that was really good. We worked through University of Utah for a couple of years, couple of funding cycles. And then also at the same time had got a group from Rutgers who run this place called WinLab. This is still happening at WinLab. They have a big indoor testbed, indoor and outdoor radio testbed called Orbit, which I don't remember what it stands for. But it's a big building. The Orbit building is probably, I don't know, it's like at least 3 times the size of this room. And it's got all these radio nodes hanging from the ceiling and all kinds of equipment in there, including even today on, I checked before I came, there's still USERPs in there, and there's big USERPs and small USERPs. And so they were actively doing that research. So I think there's more, if we had people who were interested in this, I think there's money that could pay for developers if they want to go work with those guys and produce something that they're interested in, and we could feed it back. I also I ran later into, through BBN, had a DARPA-funded thing that they wanted my help on. That was also a nice way to receive money, because again, it was simple. It was like, here's 1,000 hours, for the year, do 1,000 hours in a year, and here's what you want to do. And it was really, with regard to low friction about getting money, not a whole lot of paperwork once you've got it set up. So anyway, and then there's on and on and on. So the point being that there are ways, and Ralph and I and some others have started talking about, well, how do we fund this? And how do you fund it in the European context? What you do for different organizations. How do you fund something that you want to exist? I mean, we've got the example right here of FAIR, which is whoa, 3 billion euros or something. So, and I think one thing I see is that there's definitely people that want it to exist, right? There's they can tell a story that is really yeah, we want it to exist, and it's going to make it better for people, not just us or the researchy people, right? They're going to no, you're going to have your medical application or whatever else. We'll understand stars. And so there's how do you sell that idea? And I say that in the kindest and gentlest mean of enrollment or speaking and having people be enthusiastic about whatever it is that you're after. Okay, that's the story on funding. Again, there's a pattern here I think that we can repeat. It's not, But the point being, really nice to have money to pay for developers. And I know that at some point we can, yay! And we don't want it all coming from one place. We want lots of people involved and pitching in. So anyway, I do think there's ideas. I think there's conversations to be had, but it also just takes people to be in relationship with people, calling and seeing. And particularly, I'm not sure right now. Again, I've been really away for about 14 years. I've been kind of keeping an eye on the project. In one sense, the way one would keep an eye on their adult children, which is it seemed like they're doing all right, you know, and so I'm like, I don't know all the details, but I don't know, for example, how well are we doing in the academic community, right now? Are we the number one choice when people are like working on the digital comms and they're working on a PhD? Are we the tool they use? And if, I don't know, but if not, what are they using and why not? What's missing? Is it too hard to use, or is it, whatever, like that. So, okay, community building. This is another part of it. One thing that made the whole thing go. So one of the things when we started it as under the flag of the Free Software Foundation, they provided a bunch of infrastructure, which included, we'll announce your project to our big mailing list, right, to the general mailing list. But then they had, they'd build you a mailing list, and they had suggestions for how you ought to do this, thing, because we've done it for a long time, how you ought to manage your code, and how you ought to make releases, and they ought to be like this. And there's like a bunch of stuff that is, in one sense, great, and how you want to, what's your build system. And they were like, try it this way, because we've had a whole lot of experience. And again, part of it went back to an era that was before there's only 3 processors, and 3 operating systems. So some of that stuff, if any of you have been around the AutoConf universe and went, oh my God, it solves all kinds of problems that the modern things that most people use today, like CMake or something, do not even begin to touch. Like if you ever try to compile for the host and cross-compile in the same build, it's impossible with CMake. It's a total pain. Where AutoConf and AutoMake, it's all that, it just works great. Anyway, that's my pitch for that. There's not to say that there aren't other options that have come, but let's not forget the stuff that did work. Now, on the specific part of community building, I'm, as a much younger person, I was not so much of a kind of happy 11 people person as I am now. I was mostly about, why are those people talking about the weather? I'm a kid, and you're looking at your parents and their friends talking. It's kind of like that. I like things, And then eventually I just discovered I like humans. And part of it was with NSF funding. Part of it was like, okay, you're getting this money from supporting science and academics. So I turned out that one of the things I ended up doing was making sure that anybody who was using it had support. And at one point, for a couple of years, I was personally responsible for 20% of the traffic on our GNU Radio Discuss mailing list. Yeah. Yeah. And it was good. I mean, I preferred the mailing list as a way to survive because at least it was archived. You could point people to it. I know you guys are really loving the chat, the matrix, but it's not as indexable or searchable later, right? Anyway, so there's about that and again, it was like answering questions, being helpful. The other thing was about going to the PI conferences for your particular department of NSF. Those were really fun. First of all, you meet all kinds of people that are doing really cool stuff, and I was at one that was really surprising because people had known, and it was a part of NSF that was called CISE, C-I-S-E, which is where our funding came from, both places. And I was at this one conference, and there was the other PI stood up and said, "Give Eric the money." They were so happy for what we were doing. I was like, "Wow, that's pretty funny." Anyway. But community building, it's like talking to people. I mean, talking to people. How are they? What are they doing? How are they? Even if it's you guys here at GSI and FAIR were never on my list of the likely users of GNU Radio. And then I find out indirectly that, oh my God, you've been using it to run some particle accelerator? How does that work? So there's that whole part, and then now I'm here because I'm curious. And, besides, I think it's really cool. I like big, complicated, expensive engineering things and science and physics, all that good fun stuff. So there's a part, and I think this doesn't happen just like one person. It's about, there's some basic stuff that goes beyond the checklist that everybody gives you. It's about really caring about people and talking to them and what are they in and encouraging and finding out what would you like, what do you want to do or what's your crazy idea? And then answering questions. And then part of it is trying to build out infrastructure so you don't have to keep answering the same question over and over and over again. Because otherwise it's really kind of tough. But that's what I have to say about. Any questions about this? I think this was crucial to the success, actually. Because otherwise, I mean, you can't just sit in your garage or whatever and do this and not talk to anybody and expect to end up with a thing with users. All right, now remember, this is not television, so if you got questions, you can, raise your hand, we'll get you a mic. Yay! yeah, okay, great. And you wanted to, yeah? Okay. You're just stretching. Okay, but really, like I said, I'm totally willing to. I once, as a side note, I once spoke at a place called the Vanguard Technology Transfer Institute, which is kind of like C-suite kind of people, CTO, CIO kind of folks. And the way that they ran their events is that if you were a speaker, you got a 10-minute head start. And then everybody in the audience has like a push-to-talk mic. And the rule is they give you a 10-minute head start on your like 60-minute window, and then they can just butt in. It was super fun. I mean, it was like, if you like that kind of engagement. Anyway, I'm trying to drum up some here, just a little, but anyhow, let me know. Okay, and there's some acknowledgement. I have more I want to talk to that's more a little bit about the future. And again, on the future stuff, I really do want people here talking, because I've got some ideas, but I've been kind of away, all right? But I got my, welcome to the Academy Awards. I got my list of people I want to make sure we call out. Now, some of these are in kind of chronological order, just to kind of, these are people from the beginning of time. So there's Matt, who I spoke to, and then Jonathan Corrigan, who worked with me for a long time. And the thing about Jonathan I really loved was that he knew what production code was. He had worked at Intel. He had, managed the production of, making of production code, which is like well tested. He knew what a customer was. So it was like really good to have that kind of person around. He managed our releases for quite a while. He also kept my head on straight about many things and taught me about how to relate with him and some other people in a way that's, maybe more pleasurable than my possibly like over-the-shoulder unsolicited code review, And he did a lot of work on both the 2 series and 3 series code bases. And then later, after I was gone, he's had a stint where he was serving as the chief architect starting in 2016. So again, it's really, you just can't do this. It's not a stretch of it alone. I mean, I did write most of the original code base, but I did not build it all, and it did not reach the scale by like sitting in my office. The next person I want to say, again, these are kind of chronological, is Tom Rondeau. So I met Tom when he was a graduate student still at Virginia Tech. And I went down, because Virginia Tech has a pretty good community. There's a lot of people coming out of there that know something about digital comms. And he took over. He was my hand-picked successor, basically. We had at that time, had effectively the benevolent dictator for life kind of a role model for leadership, which kind of works out. Somebody's got to make decisions about what goes in the code and what doesn't. Even when you go to another organization, you still, somebody or some buddies have to be saying yes or no, and they may just be saying no, but it needs this, and then it would be okay. Otherwise the thing turns to mush. It just turns into a big mess. And then I also wanted to thank him for his continuing to support to the GNU Radio and GNU Radio community, even after he was long gone leading the project. And then basically we kind of go down to the other people who have kind of headed the group. So there was Ben Hilburn, and he took the lead after Tom, and then he was part of the reorganizing the whole leadership structure, where we're going to retire the benevolent dictator for life, which, yay, go General Assembly, right? Marcus Miller right here for serving as the chief architect starting in like about 2018. Are you still technically that? No. Who is the chief architect? Okay, right. And Derek Kozel, who's not here, but he ran it also, right? Was he the president of for a while? And the co-PI to SETI, which is like, again, when I heard about that, I thought, wow, that's an interesting arrangement. And I did go out and tour the SETI facility and like I had a scheduled, knock on the door and get a tour on the inside. It was really kind of cool. It's a big, it's the Allen Telescope Array. It's up in a really quiet valley in Northern California. It's kind of fun. And Josh, the current president, yay, Josh, yay, Josh. Again, I have to say that it really, my heart goes out to it because there's like a lot of, there's like, leadership. It's like, there's like, somebody's got to like raise their hand and say yes and kind of, talk to people and make the decisions. And, and it's, again, it's never just that there's like one person doing it. And then really there's a whole bunch of long-timers that have been around GNU Radio, like from when I was here, and some of them are still around. And there's like Martin Braun, not here today, and Phil Ballister, and Mate, who was doing Debian packaging forever and still doing it. And there's more, but there's some people that have been around since I left and it continued. So that's, for me, quite interesting. And then Ralph, and part of the, in one sense, the new crew of people, the whole FAIR team, the people, oh my God, they're using GNU Radio, something about a particle accelerator. I'm also looking while I'm here to hear more about like, which part of it are you controlling? I mean, I can kind of get event capture or whatever. And what that brings is like, oh my God, so you have like safety critical stuff. Oh yeah, you don't want to break the machine, or, I'm assuming that keeping people from being irradiated is handled by some other things like concrete and like stuff like that. So anyway, many of you here, I don't know many of you, but I really do want to get to talk to everybody while I'm here for the week. And I've talked to some just random people so far. It's like, what is your interest and how did you get here? What, if you're using GNU Radio, yes or no? Interested, like talking about RF? Okay, good, that's in the territory. And the challenges around like, hey, how do you do real-time control of this really big, accelerator? And it's high power, and it's like, sparking against the wall, and you're like, not what you want. So that's what I have on that. And I'm sure there's people I missed, but I wanted to just leave you all with a sense of like a gratitude, that including those of you who are just here for the first time to go like, well, I just kind of came to find out what it's about. So again, we have the track that is for people. We've got a whole track for those people. Yay, Ralph and team. So, all right, and now looking to the future. This really, I'm not kidding, we want like audience participation here, okay? Okay, so here, what I've got is a couple ideas or thoughts. But basically, we're at a transition stage right now. We have built, again, there's only been a couple. And there was like the 0.9 to 2.0. At that point, there were very few users. It was no big deal. It was definitely an improvement over what we had before. And then there was an evolutionary step from like 2 series to the 3 series. I mean, everything, a bunch of stuff changed. We made breaking changes, but it was kind of this evolution. We are really at a point where we're proposing big changes, and we want to know, partly we're here together to the week on at least the 4.0 part of the gang to like, are we building something useful? Is this going to work? I'm sure it's going to work for FAIR because you guys are here and it's going to work for you. But is it going to work for the rest of us? That's kind of like, and I don't mean that glibly. It's just kind of like are we building something useful? Okay, so what, anybody have anything to say right off the bat? Okay, I'll get you a better question. So I've got some questions that are in this category of who is currently using GNU Radio? What communities are using it? And again, this probably varies depending on what continent you were on. Oh, look at that. Yay. Okay, give that man a microphone.
Someone has to talk, right? So we do have, of course, still academia. We're like the #1 thing where people go to when they need to teach a modular SDR approach to students. We do have, obviously, the big kind of research things. Well, FAIR. We do have satellite
yes.
ground stations. We do have air control stuff. We have a lot of automotive people that start to experiment, or long time ago already started to experiment with things like fleet management, right? So we're going more industrial, I guess, in total than we used to. What I think has decreased a bit over time is the number of PhDs that primarily do something on radio, which is simply because the trends, right? SDR was the big OO's thing, right? Mitola and everyone
yes.
after him basically swam on, and that was obviously great for a free software SDR system. And we're kind of, trying to find a niche there again, right? Some things are really just harder. We're on a PC, even with GR4, we might not be doing the bandwidths that a modern cellular system does, because, well, the channel coder doesn't get any easier.
Yes.
So that is still super interesting. Then, but what we're really good at is the whole fusion thing, where we have, well, this is a big 5G, 6G research topic, is like joint communication and sensing, where people are actually looking into how do we do the communications and also know where the pedestrians are and also know when to brake because there's a car coming around the corner, kind of things. And these things are where, well, you can do that literally like very well in say, MATLAB simulation, but you're going to write a lot of MATLAB code.
Yes.
And nobody likes writing MATLAB code.
Yep. Great. Thank you. All right. I'm going to give you another question unless anybody got an answer to this or is there anything they want to say about it? No. Okay.
Maybe we should have softened them up with some more booze in the beginning. Maybe first beer garden and then the discussions.
Yeah. So, I mean, we got about 4 minutes left here to stay on time. But I want to, and I'm going to get somebody else to speak here before we're done. But I want to let you know that I'm around this week, and I'd love to talk to everybody about whatever your interest is, because I'm kind of that kind of person. All right. This was a question. It sort of got asked and answered already. It was kind of like, who's using it, and how are they being incentivized? And you guys might have, I don't know that we need to do this right now from the front of the room, but there is this idea. This is back to how do we get people to do the work. So, I mean, there's hobbyists who will do work, and some of those have made contributions to the core of the system. And this one, I think, is one that, well, part of it is if it's teaching, learning, and research, well, research, we're in the right place, right? And then, again, these are just kind of questions, and we did kind of talk about this. But this last thing over here is like, who are these PIs or co-PIs that we know? I mean, who's using it now? Like, really, what are their names? Can we go talk to them? And can you go talk to them? I mean, I'm here just, in one sense, cheering. So, anybody have anything to say about this one? Okay, because partly what I'm looking to solicit on this is, are there problems that GNU Radio could solve that it's not currently solving? And why? Is it like there's a steep learning curve on it, or not quite right? Or there is definitely, any SDR, there is an incredibly steep learning curve, because you got to know about at least enough RF to know that there's not all linear and ideal. And then you got to know some DSP, and then you got to maybe both the theory and the practice, and then comms, the theory and the practice, and then if you're going to do the low level like new blocks, you got to know how to code. So it's steep, I know. So, and then we've got with things like the GNU Radio Companion is an idea. Well, we've got this big block set, so then you still got to figure out how to put the blocks together. And I think it's an area where we've probably got a pretty good start on it, but I think we need more fully worked examples at demonstrating this is our best idea of how to build this kind of radio. Now, I know, Josh, that in the work we were talking about, and with Danny, it looks like that's a perfect example. Is Danny here yet? Oh, yay! All right, hi! Hi. They mentioned your name when I was at SETI. They said, oh, yeah, he can get his own antenna he can use out there. Yeah, yay! Anyway, that kind of a thing is like figuring all that out. And then, okay, I got 1 minute to go. Anything else I want to say here? Oh, questions, discussion, and just general inquiry. This, I think, is really, a lot of this can just happen during the week when we get together. I care about, again, this question about who could we serve that we're not currently serving and why? And again, is there some stumbling block in the way? Is there something that's too hard or it's too awkward? I know, for example, that with GNU Radio, it's traditionally been very hard to make the transition between like the PHY layer of your radio into the MAC layer. It's kind of traditionally from a streaming-based thing into all of a sudden I have like protocol data units. I got from this to this, and it's how do we architect that such that there's a well-known, straightforward way to do it as opposed to a bunch of different ad hoc solutions. So, okay, that's it. Thank you for your time. Looking forward to speaking to many of you while I'm here for this week. I mean, I didn't just come here just to do this. I'm here to plus get the tour and, see big science on the big scale. So, again, thank you very much.
Okay, thanks a lot. I think we all need a break. There's coffee outside, and there's some drinks also here during the talks if you like to take a sip. We shifted the schedule by 15 minutes, so maybe the speakers that come next could maybe just get in contact with me, and then we could arrange how we follow up. Okay, thanks. So shifted by 15 minutes. Welcome back. I think we should start. Welcome back. Hello. Let's continue. Welcome back. We already started to collaborate and discuss, which is very, very good. But we should also be mindful about the time. We shifted the lightning talk of today to tomorrow. So tomorrow we're going to have 3 lightning talks. If you are inspired and you also want to give a lightning talk, just get in contact with one of the organizers, and then we schedule in on Thursday and Friday. Okay. We shifted the lightning talk of today to tomorrow. So we're going to have 3 lightning talks tomorrow, so they're very short format talks, 5 minutes. If you have some idea or want to talk about this, then Thursday, Friday, please approach one of the organizers and we can get in touch and organize this. So the next speaker is Dr. Stadelmann, who's basically, he's Jens. No, there's some people, whenever I say doctor, there are people that really deserve it because they actually work in the field and they know what they're talking about. And Jens offered that he's giving us a pedestrian guide to what are accelerators. So the idea is that by the end of the talk, you're all accelerator experts. Tomorrow we have the guided tour. Some of you will get lost. And if we find you after 2 days, then you're either new specimens for our cancer treatment, or we give you a job as a new accelerator physicist working on signal processing at GSI. So let's give Jens a warm welcome, and stage is yours.
Yeah, welcome from my side. So I give the, let's say, a little bit extended welcome talk. What is this place where you are, what we do here? So I want to show you a little bit why we build accelerators, very shortly, a little bit, a few examples. What is an accelerator actually, and why exactly look they exactly like this? Yeah? We have this claim you probably saw on your invitation. We explore the universe in the lab. So what does it mean? I mean, what we in principle want to do is we want to answer questions like, what are the smallest building blocks of matter, and how and why and where and when were they created? And for that, we have to somehow get the matter or the state of matter, which is in something like this was happened here at the beginning. This is the Crab Nebula, and in the middle was a supernova explosion. This is all kinds of different material and gas thrown out. You can see it with a telescope. And then we want to have the matter under this temperature, energies, pressure in our lab. Yeah? Or how does a neutron star work? How does it look in the inside? How does this nuclear matter forming the neutron star behave? This is a very, very high pressure, high magnetic field and things like that. And for this, to get matter into this, what let's say from our viewpoint here on Earth, very extreme conditions, you need a particle accelerator. And this can, for example, look like that. Yeah? You can have 2 heavy ion nuclei. So this is a nucleus of, in this case, it's gold on gold. Actually, if you're sitting on one of them, they are round, that they are flat like this. You only do it to the relativistic speed if you look from the outside. And if you see they hit each other, a lot of different new material is created. And if you want to look into this very hot collision zone at the beginning, there you have matter like in the neutron star. But then you only have a very, very short time to look into, and it's very tiny, and you have a lot of background. So you have a lot of data coming at you, and you want to find the few particles which actually have been there. Yeah? Most of the particles just can tell you, I know somebody who has been there. Yeah, and only a very few particles have been there where they were so hot and so dense, and you try to find them. So it's a lot of data you have to process. This maybe gives you already an idea. So, but how do you do that? So first of all, from the accelerator from the experimentalist point of view, they are very often would be happy with an atom. But from the accelerator physicist point of view, which I am, we need an ion at the beginning. So an ion was an atom before. You can add some electrons or remove some electrons. In our case, we always remove electrons. So you have a positively charged nucleus, and you have electrons around. If you remove a few, the gross charge of the thing becomes positive. So it's electrically charged, and as soon as you have something electrically charged, you can influence it with electric and magnetic fields, and that's basically my job. We start here, this is how it looks. It's a big place. You have here is an ion source, there's a small, and for example, the one I show here works more or less like the principle, like the neon lights from the ancient times before the LED lights, yeah, where you had a gas discharge in this nice color. And the basic principle of acceleration is super easy. You just have your positively charged ions, which is not easy to do. We have a complete group working on that. And you take a very high voltage. You take two metal plates. As soon as the positive charges see positive charge, they're repelled and they're attracted to the negative charge, so you can accelerate the particles. And this was actually done, yeah, one of the very first accelerators built, and even some used today use these DC acceleration thing. This is of course boring for the GNU radio kind of thing because it's not accelerating alternating voltage. But it has another problem. It has its limits. So the highest power supply you can normally buy gives you a few 100,000 volts, maybe a million volts, and if you transfer it to a lab, your maximum accelerating voltage you can get is 10, 20 million volts. That's it. After that, you have discharges all the time, it's not working. The world rocket is something like 30 or so, but our users, the ones which want to explore how this neutron star works they need billions of volts for accelerating the ions, and this you cannot get by this means. Now I have to make a confession. This is a confession of all accelerator physicists basically. We cheat the ions all the time. We take a very low alternating voltage and make them believe that they're accelerated by a lot on a very high voltage, but we always use the same low accelerating voltage. And this is, for example, in the case of our first accelerator here, it's RF with 36 or 108 megahertz. So we are all getting in the RF regime. How is it done? Let's just assume we have here a bunch of, I have a photo soon, a bunch of so-called drift tubes. These are metal tubes with a hole in the middle. And we put this voltage on them. And if you do it right, the ion comes out of one of the tubes. It sees the accelerating part of the voltage and gets a little faster. Then the voltage goes to the opposite sign, and normally it would decelerate the particle again. So if you put the particle in something like that with a AC voltage, it will just oscillate it forth and back. You will accelerate it a little, but then break it down again. But here, then it is, if you do it right, in this moment, it's in the next tube, and the tube is a piece of metal around the ion. Maybe some of you have heard of a Faraday cage. So this ion doesn't see the external field. So what it does, it just drifts with a constant speed forth, and then, if my colleagues from the linear department did everything right, if it comes out of this hole, there's again the same voltage accelerating it a bit further and further and further. And by this means, if you make this drift tubes longer and longer because it gets faster and faster, you can accelerate in principle to very, very high energies, and even could do this experiment with the neutron star. If you have about 1 or 2 major power plants and a lot of taxpayers' money, because this linear accelerator would be kilometers long and use gigawatts of energy. So this is something you can do for, we call it low or medium energies, but in the case of our accelerator, which is right over there in the next building, so we are here, and it's over there, 130 meter long, so it's just the other opposite building, you can get to something like 20% speed of the light. Yeah, and then we go to circular accelerators, but first a picture inside. It's actually very funny because Sharp is on it. It was done by public relations. It's just the official picture of the Unilac, but I like it very much, so I put it in. So this is part of this linear accelerator, and more importantly, that's how it looks in the inside. Beware, if it's operating, you don't want to be standing there, first of all, due to the X-rays, and moreover, because it's completely vacuum emptied of air, because you can, of course, not try to accelerate your ions if it's all full of air. It's a little bit like you want to do a dash world record in a crowded space. It doesn't work. You need free space to run. So that's why we evacuate them. But here in there, in this little thing, there's an ion beam, and there you have the drift tubes, and actually this complete thing is an RF system. So, it's the first stage. Huh? This has stages. Is this a pre-stage and then 4 stages? And the funny thing, it's a nice question. Actually, we can operate them. We can leave something away, so we get different energies. So you can accelerate to a certain point, and the rest is switched off, and then the particle drifts. And that's why our users, even behind the linear accelerator, can get the particles with different energies, which is quite important to them. They don't want to not only want fast and many particles, but they want them at a distinct energy, which is not available on all accelerator labs. Yeah? And here we do something like the same trick. So we take the beam from so you need the linear accelerator even for the ring accelerator, because we inject the beam. And we have here a structure made out of these red things, we call them bending magnets. In principle, it's a big magnet, north and south pole, and if you shoot then a charged particle in, it's deflected perpendicular. You maybe remember that from grad school or from high school. Yeah, there was a rule with the fingers and so on. So most of the structure is meant to bring the particles back to the same point. The yellow ones are magnetical lenses, because as in any optical system, the particles tend to drift apart, and you have to bring them back. Otherwise, they will hit your vacuum vessel and be lost. It's something we want to avoid. It's actually something why we need exactly to know what the beam is doing, and GNU radio comes already in the game. But first of all, we want to bring them back to the same place. Why? Because we have an acceleration cavity, we now call that. It's one place we can put RF on the particles. And then again, it's the same trick. If they are here, they see the accelerating part of the voltage. And if they are on the other side, it would be the decelerating part of the voltage. And by this means, we can make them faster and faster, round by round. This comes, of course, with new problems, because these ions, they get faster and faster. Therefore, the magnets have to get stronger and stronger. It's like if you drive your bicycle or your car. If you go faster around the corner, you need more force to keep you on track. So this is why we have to ramp up the magnets. And now comes a real nightmare from the RF point of view. At this, from the high energy physics point of view, still low to medium energy, they actually change their velocity. So the frequency they arrive at the accelerating cavity gets higher and higher too. So we go to our RF engineers and tell them, yeah, we need a high power RF system, but we want it to change frequency in a very controlled manner and fast. And if you know, many of you are RF engineers, what you want is a stable system which never changes frequency. So they are very mad at us, but we give them a lot of beer and so on, and so they still build it for us, and that's why we can accelerate the particles. So that's actually where the name comes from, because you have to be synchronous with your RF frequency and your magnetic field, otherwise you get no acceleration. And then if you have accelerated enough, either to the limit of your magnets or to exactly the energy the user wants, you can extract the particles towards the experiments and smash them on something and create matter in this very extreme states like we have in the universe. That's how it looks from the inside. You have here this bending magnets, you have here the magnetic lens. This is already in higher order. It's something like you have a cylinder at your... Please. We can,
sorry for the
for the outsiders. Yeah. Well, I can repeat it. The question was: do we have to accelerate them plight, or do we have a signal? We have actually several signals. You can have put a transformer at some place of the accelerator, and there you can measure the particles going through. It gives you a current. What is much more interesting for us is actually we have kind of plates along the accelerator, and there we sample with very high frequency the electric signal which is created by the particles inducing space charge into these plates. And if you sample this with a very, very high bandwidth and very fast, and you do a Fourier transform of it, it actually gives you the revolution frequency of the beam. It tells you the energy spread, so how good you hit your energy or if you have strays. And it even can tell you something how often they oscillate per round around their from us wanted orbit. So there's a lot of information in that, and this is something which Shahab is total expert in. Getting the signal, he even got the PhD for the something like that, and and he can tell you in the order of 10 to minus 6 to 10 to minus 7 the revolution frequency of these guys in the ring. And from that, for example, even later in an experiment, if you put them in a storage ring, you can get the masses of the heavy ions, or the fragments of heavy ions, which is then a very interesting information for the physicist, because with a very often quoted, I would say, most famous equation in physics, E equals mc square, it's a binding energy. So you can make very exotic matter, put them in a ring, measure the signal, and it tells you what the mass is and the binding energy. So there's a lot of signal processing involved, otherwise we go blind. So thank you for the question, perfect question. Yeah, so what we do with it, 2 examples, very fast examples, I will not go into detail. We developed a cancer therapy with heavy ions here. That's what maybe some people read in the newspapers about. So we treated over 400 patients here at GSI with carbon for tumors, mainly in the head areas. It was so successful that a dedicated accelerator was built by us at the Heidelberg facility. And back to basic science, this is basically our mission. We are a basic science lab. We created quite a few of new elements in the periodic table of elements. So it's what you know maybe from your chemistry class in school. And here are some with a distinct color. I think they even come up. It's the element 107 to 112. They were actually firstly created here at GSI with our linear accelerator, and they even got named by the science group. It's 107 borium, 108 hassium for the federal state of Hessen we are in, 109 meitnerium for Lise Meitner, very famous German physicist, Darmstadtium for the city of Darmstadt, Röntgenium for Konrad Röntgen, he invented the X-rays or found the X-rays, and Copernicium for Copernicus. So there you find them in any chemistry book on this planet. So Darmstadt somehow left the mark there. And this is the nucleic charts, or the periodic table of elements for the physicist. In one direction is protons, in the other direction is neutrons. And these black ones here are the ones which you can find in nature. And all the other ones are the ones our scientists want to explore and do science with. And quite a lot of them, the orange ones, were actually discovered here at GSI. Moreover, most of them can be produced here. And as nature usually is, nature is never fair. The ones which are most interesting are the ones which are hardest to produce and live only a very short time. And that's basically why we built the new facility, because we want to go further out here in all directions to go to we call them exotic matter, which is more interesting for the users. So how we do that? We have we want to extend our worldwide already worldwide unique accelerator to new capabilities, and this will look like that. Yeah, this is the present facility. This is our construction site. Most of the civil construction is done. We are in the south part putting in right now the building infrastructure. In the north part, it's building infrastructure and already parts of the accelerator you will see tomorrow. And what we want to reach is, we want to reach a factor of 100 to 1,000 more intensity of the primary beam. And for secondary particles, the ones which we make out of the primary beam by smashing it on some wall or some target, we call it, even a factor 10,000, but a 10 more. Moreover, we can go a little higher in energy. That's interesting for some physicists too. So the question is how we do that. I mean, it's not that the present facility is not running at full speed, so we have to have ideas how to improve that. So, of course, you can upgrade the existing facility. That's done continuously. We have actually at GSI, our uniqueness is that we are a heavy ion lab, so you can, as an experimentalist, you can basically order any ion from protons to uranium. So the stable ones you can have from the source in the accelerator accelerated on your target. You can even have different energies from shot to shot and even different ion species from shot to shot. So you can have a user who gets a nickel and the next one gets a gold, shot to shot. And then even if you created fragments, you can store them in storage ring and keep them for some time and investigate them as long as they live. It makes complete sense, because if it's hard to produce a particle, it's good to save it as long as possible and investigate it. But what does more intensity bring you? Come a little bit how the science here works. It's publicly funded science, so if you have a good idea and want to do an experiment, you can go to our Experimentausschuss. There's smart people, actually our scientific concurrence guys from all other labs of the world, once per year, and you propose what you are willing to, what you want to do. And then they have to judge, is it feasible, is it not feasible, is it best done at GSI or somewhere else, and is it, of course, interesting enough to be granted beam time, we call that. So to get that. And this is all a yes. There might be even one more problem. It might be that what you propose is super interesting, but it uses a lot of beam time. Yeah, to get the right signal, the right amount of statistics, well, maybe would need the complete accelerator for half a year. And then they would say, sorry, no, we have so many users, we cannot do that. But if I can increase the primary intensity by a factor of 100 to 1,000, you can do it in 2 days or on a Saturday morning. And then suddenly things become feasible, which were not feasible before. So it's not just a mere factor or something, it opens up gates to new physics which you could not explore before. That's why it's interesting to increase the intensity, but factor 1,000, how you do that. One of the things is, of course, improvement. Then we made already the existing synchrotron faster. It's 10 times faster now. It's already a factor of 10, so it could give you one beam. Wait for the microphone for outside users. Yeah.
All right. Yeah. Thank you. Just out of curiosity, because you mentioned 90% light speed with the current facility,
yeah.
Will this change with the new planned one?
Yeah, this will go a little bit faster. It goes for protons then to 99% or even so. But at a certain point, yeah, they don't get faster; they just get heavier.
Ah, okay, yeah, that makes sense.
Yeah, the CERN is still at 99.999% of speed of light, but so in the speed difference, it's not a big difference, but in energy, it's a lot. Yeah, so what amount of energy you put in? That's why we usually, unless it's an outreach talk or for non-experts, we always talk only about the energy of the particle, because it's about, there's a capability of reactions it can do, what particles it can produce if it hits something. Yeah. But at least here, the speed still gets considerably faster, and even with it, one a little faster. No. But my point is why you do that. So as we started this business in upgrading, we could deliver beam once in 3 seconds to our users. With all the upgrades, the present machine, the synchrotron, can deliver beam 3 times per second. So it's roughly a factor of 10 faster. Actually, it's not usable in this speed by the present users, which are all here, but it's good as an injector for that one. So it's the first factor of 10. And then we leave a stripper. It's just one example. So why I could explain all the rings and why they are produced like that. It takes over 1 hour. I did that as a German outreach talk. But I want to give you one example what gives you an improvement, why you do that, and why you need a new accelerator then. It's that we leave a stripper away. Well, it sounds a little bit sleazy. Does it mean? So if you accelerate your charged particles, they come out of the ion source with a certain charge. For example, in case of our design particle, the uranium, it's 4 plus from the charge. It doesn't mean that all the, from the source, it doesn't mean that all the uranium created in the source have the electric charge 4 plus. There are 2 plus, 3 plus, 5 plus, more of them, but you take the most abundant one and the others are already lost. And here's exactly the point. Whenever you choose a charge, you lose all the other charges. So then we accelerate a little bit in the linear accelerator, and then we actually hit our beam on a gas jet in ultra-high vacuum. That by itself is a technical marvel. So you let gas fall into the ultra-high vacuum, you hit it with ions, you pump it away, and the ions still think they are vacuum, but this short place, and then they are due just kinetic interaction, they lose more electrons. And it again gives a charge distribution, leaving us with uranium 28 plus as the most abundant one. That's already a very strange system. You have uranium 28 electrons gone, so the usual chemistry lab cannot do that anymore. And then we accelerate them further, and shortly before we inject them into the synchrotron, we hit a thin foil, and again we strip off charges, and the most abundant charge state is 73 plus. So you get a distribution like that. So it's not like you change and you get all the same outfit. No, you change and you get very, very many different outfits. So if you stay with soccer, you have Barcelona, Bavaria, Madrid, Rome, and so on. And you only can accelerate one of the teams. You know how it is with fans and one bath. So we have to choose one. And by this, we throw 6/7 away of the beam. By just leaving the stripper away, we gain another factor of 7. So with the increased speed of our present machine, and this measure already gained a factor of 70, but I end up with a highly charged beam. It's higher intensity, okay, and it gets even a little bit more stable. It's a little advantage. It's for the experts, has less space charge, but it's not. But you cannot accelerate it as easily. So the maximum energy you can get out of our present machine is too low for the experiments. That's why you need a new accelerator. So we don't build the new accelerator just for fun. In principle, we need it to get this high intensity beam to more or less the same energy as before for the same experiments, which bring you from, we need half a year to a Saturday morning. And for this, we built the SIS 100. It's over there on the construction site. The tunnel is built. It's actually double tunnel, one for the accelerator, one for all the devices, power supplies, and so on for the different devices in the machine. And you get an additional benefit. You can even go higher in energy. You can even accelerate protons as far that you can produce protons and antiproton pairs. So even new physics opens up, which was not possible at all with the old machinery. So you have the same thing we are doing right now, much better, but you have new things in addition too. Basically, as a trade-off of the machine, you have to build anyway to fulfill the first capability. So this is one of these designs. Of course, you see a lot of storage rings. Here's a storage ring. There's a storage ring. We will see one live tomorrow. Sharp is one of the world experts in the storage ring business. So if you are there with him in the ESR, I'll ask him lots of questions. He knows everything about it. And especially he knows what signals the storage ring can deliver and what you can do with it. And there comes no radio in. So my message to you is, yeah, you're here at Guest at the world leading science center. We build accelerators a little bit for fun too. Yeah, I like to operate them. I try to improve them. But of course, we get questions and requirements for the beam by our experimentalists, which uses facility. They come from all over the world. And this basically gives us interesting tasks and challenges which we have to meet. And for that, we have to process lots of data. And you saw, we're putting RF into our machines. And if you look at a single spot of an accelerator, you have bunched beam, we call that. So it's not a continuous beam. These are always packets of beam passing by. And this is actually, if you look just at the plain physics, it's RF. So we put in RF and we get different RF out. On there, we have very many places GNU radio can come into the game. And thanks to Ralph and his team, and Shahab, and we was more a little bit on the experimentalist side, we use it at very many places already. Yeah, all our we modernized all our RF systems. A lot of software-defined radio went in, and old analog devices were thrown out. And of course, we process the data coming out that the physicist at the end can write nice papers about cosmic matter, which has not been investigated before. So at this point, I want to thank you for your attention, and feel free to follow us online on several places and give your comments, post your photos, ask questions, and of course ask questions to me right now. Thank you.
I'm a frequency stability person. And 2 slides before the end, if you go a bit backwards, back. Yeah.
This one?
There's a few mentions of 0.7 Hertz, 2.7 Hertz. In general, what are the frequencies? So you mentioned 140 something megahertz, but so what is the stability and what is the kind of frequency that you're handling?
So we have different frequencies involved. Actually, the linear accelerator runs in a 50 Hertz mode, so it makes one bunch of particles with every periodic time of our power grid network. So it's synchronized with the power grid network. To accelerate it, we use 36 megahertz and 108 megahertz in the linear accelerator. And in the ring accelerator, we use frequency from 500 kilohertz to 5 megahertz with 2 different systems. So it's not the same system. One has half the frequency of the others.
And these are frequency that you feedback as a function of your ion acceleration capability, or are these high stability local oscillators?
Actually, in the LINAC, it's a high stability system. Even the LINAC itself, this tank I showed to you with the drift tubes in, it's part of the accelerated system itself. It's the oscillator actually.
It's an oscillator. Mm-hmm.
Yeah. On the synchrotron, because you have to change the frequency, it's basically a transformer driven with an RF power supply. Yeah. So that's, and of course there are means done to get it somewhat in resonance. So we change. There's a big stack of ferrite in, and you can change the pre-magnetization of it over the cycle. But in principle, even our RF guys say it's a fast transformer. Yeah. But of course, the source is a completely valid RF source with a software-defined radio before thing. And there, it's all not directly on feedback. Actually, I didn't talk about that, but we are, of course, working on feedback systems. We have even experts here which stabilize the beam. You can even, in the storage ring, there are different means of cooling. I will talk about that tomorrow if you're there, but one of the means of cooling is actually look at the displacement of the beam, take this signal, invert it, put it back on the beam to somehow push it back on the other side. It's called stochastic cooling. It's such a clever idea that it even gave a Nobel Prize to an accelerator physicist, to Mr. van der Meer in 1984, 85. Yeah, so there are lots of more of RF signals which are used, or feedbacks. Yeah, but the main accelerating voltage is more or less steered. You give a ramp in amplitude and frequency, and we run that over the cycle. But some accelerators use actually feedback on that. They measure the magnetic field and follow with the RF.
Maybe I can comment on that, on the challenge, especially for the CIS 18. I mean, like when the particles are very slow, You need a very low revolution frequency. But when you extract them, you need up to 10 megahertz. Now, those of you who have built a phase-locked loop, be it digital or analog, you all know they like not to be moved, so maybe you can change them by 1% over a second. These PLLs, or these frequency drivers, these DDSs, have to change frequency from, for example, 200 kilohertz to 10 megahertz within 100 milliseconds. And if you have a too high phase instability or noise, you start shaking the beam, and protons or ions, they're a bit like elephants. Treat them bad, and they will never forget you. So they're basically, the size of the bunch will become bigger and bigger and bigger, and you can't easily cool them. So we have to handle all the beam parameters with highest, most care to keep the beam small and very precise in their transfers, but also longitudinal dimensions. Also, I like your PG explanation of stripper. I was a bit worried because if my wife is watching at home. There's also like a non-PG version of explaining it. One of the issues why we want to minimize the stripping is it's basically like if you have people who take off clothes, sometimes get ugly and people take more and more distance. So the problem is the more you strip those particles, the more space they occupy and the more they repel each other because they don't like each other. So to keep everything PG, we say like, no, let's strip as little electrons as possible because this allows us to put more particles in the same spot in the accelerator, and that's one of the ways how we accelerate to very high intensities. But to keep this only partially stripped ions in the machine is a delicate thing, and you can ask some of my colleagues on that side. That's the reason why we have ultra-high vacuum systems to make sure that they not lose any electrons while being accelerated. Any more questions?
What is your frequency and timing reference for the accelerator?
Which frequency?
How do you generate your frequency? Do you have atomic clocks or GPS stabilized?
Yes,
or just
we have
phase-locked loops?
atomic clocks, and the synchronization of the accelerators actually is GPS stabilized. So because you have not only the clock for your RF, but you have to sync different clocks over the campus if you want to shoot from one accelerator to the next, and this is GPS synchronized. Its name is White Rabbit protocol. Okay. So you can give timestamps to your things and start the accelerators at the right moment. Because if I am ready with beam from the one synchrotron and Shahab is waiting at the storage ring with the storage ring for beam, the bunch length is 300 nanoseconds. You have to be quite exact in time that it finally reaches the next ring. That's is synchronized with GPS.
But you have a centralized frequency that you distribute.
Yeah, exactly. Yeah.
Okay.
So it's two. Yeah, the individual machine has its own clock, but then there's this centralized White Rabbit system which synchronizes the machines.
White Rabbit, for those people who haven't heard this is like a P2P standard on steroids. So you synchronize this down to below nanoseconds, picosecond level.
Yeah, thanks for the interesting talk. What's happening on the detection side? So at the collision, what sensors do you have there, and is GNU radio used there? What are the key parameters?
It's actually a hard question for me. I can explain you in principle what sensors they have. We even will see one tomorrow. We will walk in. You have actually a stack of different sensors. One are so-called multi-wire chambers. There's like gas-filled chambers with some wires in, where you can then in the gas, your particle going through makes a little bit of ionization. The wires suck out the charge, and then you look on both ends of the wire for the signal, very tiny signals. You have to amplify them. You have very many wires, and then you can reconstruct the path. Other things are just at the end of the path are CCDs, like you have in the camera of your phone. But actually it was the other way around. They were invented for particle physics and then went to the camera. And you have a lot of scintillators, so you have special materials. Most of them are plastics with some exotics in, cesium or so. And then if a particle goes through, it makes light, and then you put light amplifiers on both sides, do the same trick from the difference of the signals. You say where it passed, you know your geometry. But at the end, what you have is big data. Yeah? You have 10,000, 200,000 channels. And right now in the experiments, like we have them here or at CERN, for example, they still trigger. So they have some signature on when does something interesting happen, and then they write away all the data, and it's already that amount of data that you don't see that much online. They have some signatures, but it has to be processed offline, so you have 4 weeks of beam time and 2 years of data evaluation. In the future, which is completely crazy, we have a group here for the detector, which will go here, CBM. They want to leave the trigger away because they always say, oh, you never know what might become interesting in the future. You want to have all the data. If there's new physics found, we can look into our old data and see if we can find it. It's a neat idea, but this gives them something like 1 to 10 megahertz per channel times 100,000 channels all the time. So there's a lot of computing effort in them, but we have already a prototype running. So not with 100,000 channels, but with quite a few, let's say 100 or so. They do it in the existing high power computing facility. It's very strange because they just fire the data away and it's basically lost in the data nirvana, and then they have to search it again with algorithms. So it's quite interesting. So it's very new technology, and yeah, it's not my field obviously, but it's interesting.
Maybe I can have also a comment here. Thank you very much for different type of detectors or sensors, as you just mentioned. Of course, among the many different types of particle detectors that we have, they are working either in the DC range, or they are working on some of them. They may have pulses. Some of them may be counters. Some of them may be, as Jens just mentioned, counting scintillators or whatever. But some of the detectors, they are inherently RF detectors. So that means they are particle counters, as you just mentioned. They are particle detectors whose primary output is an RF signal. And these ones are specifically very interesting, as Jens just showed, for the storage rings of all kinds. You see every one of those rings that you see here is specifically interesting for this case, because what you are interested in is to see either the position, you can imagine it's like a donut. So it's like a huge pipe, donut-like pipe, where the particle beam is traveling inside. And what you want to do is that you want to know exactly what the position of this beam, this needle of the beam is with respect to left and right and up and bottom, because this is a very important information in order to correct the magnetic lattice and do all sort of connections. Or if you want to do it, use it for a tumor therapy, and the location of the beam has to be known. Or you just want to measure the frequency, revolution frequency, or you want to have the beam intensity. So there is a huge amount of different information that you can get from these RF detectors, because these RF detectors are non-destructive. That means they are really just kind of antennas around it. You can be I really hate the name antennas, because they are not really antennas. You can consider them as a secondary loop of a transformer whose primary loop is the particle beam itself. So this is a type of detector that also comes into. Maybe I'm going to talk about that in my flash talk on Thursday. And this is something which we are using, because this continuously gives us a signal from the beam. And suddenly, if there is a change in the beam, be it in a nuclear physics side or the atomic physics side, or just because of bumping into some rest gas molecule, we immediately see that in the frequency spectra. And this is where basically finally GNU radio comes in, because we need a kind of a very versatile data processing, online data processing and offline data processing. So while we are recording everything to the disk and sending them over to the great green cube over there for data processing, at the same time we have an online eye. Just by putting a the graph over there, just take a branch and start to make a Fourier transform and make a, for example, conditional signal on it. So GR is going to help us. It is, but it's even more going to be included in our workflow in order to make this kind of measurements possible directly from these RF sensors. Thank you.
Yeah, I wish I would get like $1,000 for every time I've been asked, like, why GNU, why radio? Actually, interestingly, when we talked also to digital comm guys, maybe we do less of digital modulation of our particle beams, but they work. I mean, like I played once Beethoven Fifth on the LAC. That also works as a transmitter. But what I find personally very fascinating is if you look at radio astronomy, for example, you look at pulsars and you get radio waves from the universe that tell you like how stars are being created. How do nebula works, how do stars explode, how do black holes merge. They emit radio waves, and we detect it here with antennas. But these are very rare effects, so you can't conclude much about physics of nature. What we're doing in our lab is basically, we build our own stars in our own microscopic black holes, if we could, we wished, but not right energy range, and we just invert the whole problem. So while it's a bit like introverted people, extroverted people, some look outside, we look inside, and trying to recreate on a small scale. But the technology that we use and also the principles are the same. Some people call it synthetic aperture radar. We call it tomography. There are lots of many analogies where, yes, how the signal is generated in the first place is slightly different, but they all turn out to be electromagnetic waves, which are captured by either narrowband or broadband RF signals. And very exciting, very exciting. So you're all experts. Now in accelerators, very good. Are there any more questions?
So I actually got two questions related to synchronization again, which is more my field. Small question first. You mentioned that the source of ions is 50 Hertz synchronized to the GPS to the grid. But that's
the complete accelerator actually. We are able to change the complete setup of this linear accelerator, 130 meter, including the sources, 50 times per second. So basically, it's like you have to imagine it's like maybe like a freight train with all empty wagons, and then the sources have to inject beams. So you can have actually of this 50.
But that's not
50 ping theory. You can have.
I get that, but that's not the actual grid phase, because
it is the actual grid phase.
Because to my knowledge, even though when I was young, the power grid was synchronized to atomic clocks. Nowadays, it's not true anymore.
We actually wait for the grid. It's actually the 50 hertz of the grid is this 50 changes of state of our linear accelerator.
Okay. I need to think about more.
It's not the RF. The RF is 36 and 108 megahertz, but this cycle that you get one bunch of or it's a few bunches, but one we call it bunch train. It's 50 times per second, and it's really synchronized to the grid.
Okay. The second question is, in the photonics community, they're used to, and there's still a bit of hype about using femtosecond lasers to synchronize accelerators. In particular, I believe that at DAISY, they actually tried and maybe are still doing that. So why is it they do at DAISY, which makes that necessary or useful, which you don't do or wouldn't want to have that kind of facility for you?
I assume the easiest answer is because this is probably used in a light source. There are a lot of synchrotron light source, something what we don't do, and even now XFEL, so you have free electron lasers, and they are much, much more precise. So we want to somehow stabilize our beam in the order of a millimeter, and they're talking about micrometers. And they, of course, have this very short electron bunches. Our bunches are 300 nanoseconds long. They are just much, much shorter. And if you, of course, want to synchronize something like that, you need an even more exact timing signal. And then on the other hand, of course, we use not only cable bound but laser bound transmission between all the assets, but not in femtoseconds. I mean, this is, mostly comes out of laser physics. There's even a big field in accelerator physics now. They actually use a high power laser to accelerate particles, electrons or protons. And then you get very, very short pulses. And again, if you have a very, very short pulse and you want to do something with it, you need this exact timing. So we don't need it yet.
Maybe I can add to that. The second question is maybe Udo, where are you? Because he's our high petawatt laser expert. He can tell you about the laser. I can tell you why, at least why we have 50 hertz mains synchronization. It's annoying. If you come from another engineering point of view, so like, why can't you make it exactly 50 hertz? The thing is, a lot of the facility is pulsed, and we're drawing tens of megawatts of power. So if you draw power, and you don't do this with the mains frequency, you get a humongous reactive load. If you have a small load, you would build an AC-DC transformer, have some capacity storage, and then have a DC-DC chopper to get to a nice frequency standard. When this facility was built, this type of storage with capacitor was not possible. So you had to have like flying wheels, which are by themselves are very complicated, very expensive, and also very, very dangerous. Also capacitor banks to buffer 100 megawatt of power. If you build this, CERN did this, they ditched the flying wheel and now have this capacitor banks to have a precise frequency standard, but they basically built 2 shipping containers of bomb, basically. So because when the capacitor flies, you store 100 megawatts over a second or so. There's so much stored energy and that's the reasons why for power efficiency and simplicity, people use 50 hertz mains, which is annoying. But what we do is once it comes to the sys18, we say like, let's wait like just one phase and say like when the time is right, and we measure this with White Rabbit. This is the zero crossing of the mains frequency in White Rabbit, and then select, now it's an opportune moment to inject. And then we can buffer this uncertainty of 20 milliseconds, we can buffer it then while storing the particles injection. There's also David Ondrejka, who has been pioneering the synchronization between UNILAC and sys18, but this is a major challenge, or let's say major interesting problem we were working on. Udo's not here, is he?
Wen suchst du?
Udo. Udo. He's our high power petawatt laser, and he knows when it comes to femtoseconds and synchronization, he is our resident expert on this. Any more questions? Maybe time to digest. Thank you, Jens. Let's thank the speaker again. Let's stop for lunch break, and maybe let's meet again 1:15 here again, and then the first tutorial will start at 1:30ish or so. But try to be a bit earlier so that we can, because we have a lot of ground to cover in the talks. So bon appétit, and see you later. Yeah, it should be on. Still have a bit of time. Hope you enjoyed your lunch and the discussions. So let's get this coding party started. I think part of this workshop is actually, the reasons why we don't call it a conference but a workshop is because we all want to make your work and to enrich the GNU Radio ecosystem and communally share and learn. And I kick off with the first a bit of introductory slides. You don't have to worry about, there's no programming exercise. This is more like to create a level ground. What is GNU Radio? We have like some people who use this for 20 years and know all its nooks and crannies and know what it's about. There are people who are new. We have people who are developers, core developers, or users writing blogs. And we have also people who are just using it for the signal processing capabilities. But we all want to share the same language, the same concepts, because that's what this community is about and what also helps to grow, nurture, and bring this whole project forward. So when we talk about GNU Radio, we don't start from scratch, but we are standing on the shoulders of giants. Many people came before us who started with the idea, fleshed it out, and there was like a time of recognition that we need to move on and to reach the next level and to think about like what we want to achieve in the next 10, 20 years. So this is like an old medieval page, like standing on the shoulders of giants, basically. Whatever you see here, I'm just presenting on behalf of the GNU Radio architecture team and for the team here at GSI and FAIR who have been contributing to it. Some views are my own, but in many cases the work, I mean like whatever is good, that's the work of the people in the architecture team and the people who contributed code and developed those concepts. And I'm the fortunate one that I'm allowed to present upon this. So GNU Radio grew organically over the past 20 years, which is very feature-rich. But we know, like with any organically grown software project, sometimes in certain parts it grew out of bounds. And there were certain branches and extensions where you would have thought like, that's not really healthy, not very sustainable, not very maintainable. Maybe I have to prune and cut down those branches that are either dead or not really necessary or add unnecessary burden. So for GNU Radio 4.0, this is a breaking change in the low level. The goal is to preserve what is good, so to preserve the same user experience on the top level, so that basically in the end, GNU Radio from for example, GNU Radio Companion point of view, looks and works the same as GNU Radio 3. So that is the view for the vast majority of users is identical. However, there were certain things underneath the hood where we need to change some of the paradigms in order to achieve a better performance and better maintenance and new paradigms that came up in the last 10 years. So preserve what is good, prune what is unhealthy, and to keep the project growing and maintainable, not just for the another 20 years, but continuously over. So it's not a fixed milestone, but it is we want to get also into a process of a continuous renewal. So, I mean, if you have questions, I can talk fast and convey a lot of information. If you have questions, please stop me and ask questions. So there are like 2 microphones, one with Jens and one with Marcus. We can add. So what are the modernization goal? Of course, it's GNU Radio. It's not Apache Radio or like Simulink. We want to preserve the community and the integrity and the large range. But in order to preserve that community, it's very important to remain relevant, both from a technical but also functional performance point of view. I mean, whatever is good, if you stagnate and you don't continuously improve, eventually people say like, okay, there's another toolkit that is more suitable for the job. So as Eric also mentioned in his keynote presentation, is like this is also like a good time to reflect upon what do we actually want to achieve, what are the bottlenecks, where do we want to move forward. And this is like beneath that, I mean, like obviously these are like high-level goals, but specifically, that's also the reasons why GSI FAIR is investing to it. We want to be able to use it in the industrial setting, also like in public infrastructure, to keep it maintainable for 24-hour, 7-day operation week. So that means we have to rely also, we should rely more on true industry standards. We have a lot of new users, so GNU Radio is used large in the academics, but also in the private industry you have a high turnaround, like many people coming and going. So we have to see about what are the pain points to reduce the cognitive complexity so that people can get more easily into GNU Radio, use it, and say like, oh, that's a good tool. I don't have any need for any other tool other than GNU Radio because it does the job well, at least to, let's say, 90% level. And that means also reducing cognitive complexity also means like reducing the learning curve. So basically we want to be able that somebody within a couple of days, weeks, is able to make use of it as a user, but also being able to contribute in a meaningful way that is also sustainable and maintainable from the core maintainer's point of view. All while this is not standing alone, but promoting a collaboration and sharing of ideas and links between academia, government, science, and industry. So this is a bit of an outline of my talk. Why GNU? Why radio? I wish I would get like a buck every time somebody asked me that question. We probably would build yet another accelerator facility with that money that I would have gathered and hired, or at least hired 3-4 full-time software developers. Then I think part of it, to motivate again, why graph-based signal processing. I think for people who use GNU Radio, that's obvious, but many people from GSI, this is also part of our internal training, is to motivate why describing signal processing problems in terms of graphs is useful and why it helps, and then going, what are the goals, the changes that we applied, and then some of the views, preliminary, what could be the next steps on the technical side, and then some question and answers. However, this one, please stop me, raise your hand at any point of time. I walk through very quickly now. If you have a question, stop, say like, Ralph, please could you elaborate on this? And yeah. So, why GNU Radio, especially at FAIR? It's a very odd question. Why GNU? Why radio? I mean, GNU is just historic because it was a free open source project, and the GNU public license was one of the first common open source licenses out there. So people say like, okay, if it's free and open software, nowadays we would call it like open radio maybe. But at that time, people chose for GNU in reflection to that this is a free software which can be used by a wide variety of people. And one of the changes that we did to 4.0, or what we propose, is to make it in some parts a bit more liberal, still preserving this open source character spirit that GNU Radio always had, but also make it a bit more permissive to be used in an industrial or public infrastructure point of view, where going fully open source in all different parts of the project is not always possible. So we want also to get a stronger relationship to the industry and government labs. And yeah, radio, I think both Jens and Shahab explained it. Software-defined radio is typically, we describe this for the shift of traditional radio frequency or signal, and now new with GNU Radio 4, also event processing, implementation from hardware to software. And if people think about radio waves, they usually think about like some dipole emitter, radio station, TV station, that emit electromagnetic waves, which are encoded, and then you receive it upon this. But GNU Radio grew well beyond just communications, but is also used in radio astronomy, where some of the radio signals are generated by pulsars, collapsing black holes. And at FAIR GSI, what you heard, we use RF both to accelerate particles, charged particles, so we have like small cavities where an alternating RF field is being used to add velocity or energy to the particle, but at the same time as the particles traverse to the beam, they drag an electromagnetic wave behind them, which at relativistic speeds is a bit like a pancake. So, and this pancake is proportional to the shape of the bunch. So obviously the bunch has a finite size, and if you want to look into the details of what is the size of the bunch in the beginning or end, looking at the electromagnetic wave spectrum is a nice diagnostic tool to measure the position. For example, if you have like two strip lines, or let's call them antenna for the argument's sake, top and bottom, by looking at the difference of the RF wave and computing the difference and the sum, you can compute the position. And if you do this at a high enough frequency, you cannot just compute the position of the center of the bunch, but also what is the position of the beginning, end of the bunch, or the momentum spread, so what is the velocity differences between the very fast particles and the very low frequencies. And this is an important feature for us at GSI and FAIR to measure, control, and optimize, and where we also use this data not just to analyze, but to feed back into our control system to improve the properties so that the particles have the right property that our experiments want. So how many of you know machine code or wrote like 8086 as machine code, like binary code? How many? Okay, 2, 3, okay. So you outed now yourself with your age. How many of you did, just keep your hands up, how many did assembler? So that is a bit more. How many did C or C++ to level, expert level? Yeah. Yeah, Ivan, please, and Matthias, please raise your hand, because they're two C++ committee members. They should know C++ because they define it. But if you look at the hands, not everybody knows machine code, and not everybody knows assembler or knows how to program in depth to a level that it's high-quality research software engineering standards. But we all need to still solve problems. So we need like tools to get the job done. And in order to communicate, flow graphs have always been a very flexible description, both from a very high abstract level point of view to express signal or even event type processing. And what we added now is to make this a high-performance signal processing toolkit where we basically put the existing GNU radio on steroids and add new concept like StudSimD, which is a parallelization, but also a modern C++ standard, while still preserving the use of Python and exploring also other platforms like WebAssembly so that you can write UIs that can run in the browsers, and support for microcontrollers and AI accelerators and TPUs. This is all very technical, but this is not a standing on its own. What also GNU Radio is more than 20 years of expertise in a large, diverse community, which is streamlined and should be ready for tomorrow. So part of it is not just because I wrote something, but it's because we share the same idea, same vision, and we want to move it forward. So that's GNU Radio in a nutshell, at least from my view. Please disagree or tell me if you think this goes too far or not far enough. Why is graph-based signal processing useful? There's a concept of mechanical sympathy, where basically you don't have, as a quote by Jackie Stewart, as a famous Formula 1 racing driver, who said, like, you don't have to be an engineer to be a racing driver, but you have to have mechanical sympathy. So what he meant was basically, more general, you have to understand and care how a machine is working, because once you know how it's working also in internal, you don't need to build a CPU or a GPU, but knowing how it works in itself will help you to get a better performance out of your machine and out of your hardware. So, and that's where GNU Radio bridges basically between the low-level programming, where you need RSIE experiences, but also the high-level concept where you want to get a job done. And just to flash some highlights, I mean, specifically for hardware software, we have to care about CPU cache, because being cache-friendly means our programs run 10 to 100 times faster. You have to think about branch prediction, memory alignment, how to handle concurrency, data parallelization, SIMD, non-uniform memory access, and notably also putting a bit of knowledge on the graph topology. So because of how I structure my problem can help me to improve the performance. And I'll come back to that in some slides later. So this is all a bit abstract, but because I thought, like, let's show like a bit of a user case example. I mean, like I told you that we use with the electromagnetic wave of particles to diagnose their position and size. And typically, if you do it naively, you put in a 180-degree RF hybrid, look at the sum and delta signal, and then directly digitize it, which some people say, like, that's the best version possible. But if you want to look into structures that are very small in the bunch, you need bandwidth of 1, 2, 3 gigahertz, which is, if you work with an oscilloscope, you get down in the bit resolution to maybe 6 effective number of bits, where this differences in position, they vary only by 10 to minus 3, 10 to minus 5, so no chance to see anything with an oscilloscope if you look at this from this part. So what do? How to improve beating the ADC effective number of bits limit? We know from ADC, there are like two limits. One is the Johnson noise or thermal noise of the ADC, and the other one is the clock jitter. And even though the ADCs of the past decade improved, ultimately they're now limited by fundamental physical limitations. And normally the rules of physics are absolute. That's the law of nature, but let's take you a bit on a ride on how we can cheat a bit and get a better performance. So yeah, if you want to get a better performance, you can either do time domain interleaving, so basically putting several ADCs in parallel, but you will be limited by thermal noise and clock jitter. Or another approach is that you use the same principle that our ear uses, like the cochlear, that you do like an orthogonal frequency multiplexing or cochlear radio, basically where you say like, I have different hairs in my cochlea which are sensitive to just one specific frequency, nothing left and right, but with a very high dynamic range. And our ear is capable to distinguish one frequency with a dynamic range of 170 dBs. So if you put two hairs, you can detect two frequencies, but with a humongous sensitivity. So why not split up the spectrum over several bands, put a detector on each one of those bands, and then basically we have the perfect broadband detector. Now, you can start building a flow graph, basically where it's just splitting the RF spectrum into multiple orthogonal frequency bands. This is just like a block diagram, how you would write it from an RF engineering point of view. And basically in this band, you get basically your classic SDR-style IQ signals, but now we do this like 32 times to cover the whole spectrum that we want to. And if you look now simulation, then you can say, because we have a finite bunch length, is actually you don't need to cover all the frequency in the spectrum, but only the characteristic frequency which is given by the pulsed RF duration that you have. And since our RF bunches are finite, you can get by just using a couple of bands where you need to look at, and then you get in blue the raw signal and in green the reconstructed signal. So this is basically a simulation, and it's basically like a Fourier decomposition. And if you look at the reconstruction error, it's less than 1%, so works. Then you start like, okay, the concept works, let's build this in hardware. And there you can see where the mechanical sympathy comes into play, because here you can see like some filters. So what we had before in the blocks, in the flow graph, you have like a hardware representation with input port and output ports. That's the reason why I also like the old GNU radio companion with this input-output ports, because that resembled, for me at least, from an RF engineering point of view, very much to filters and amplifiers that you had. But you can follow the same structure in the hardware layout with the amplifiers and the detectors in the end, like you did in the simulation in the flow graph. Now, that's like an optimization that we also apply in the software. Once you know that it works, it's like, okay, I know I have my composable blocks, but I don't need all these connectors because each connector costs money, costs RF performance, reflections, length. Let's get rid of it, and let's cast everything on a PCB. And basically this and this are the same, but this is just a higher integration density, it's cheaper to build and can be mass produced. But still you can use the same tools to simulate the performance of this, to see whether it corresponds to this and the software side. So where do flow graphs come in? So you have like this mechanical sympathy where you have an idea which you turn into a flow graph to design and simulate. Then you can first in the simulation stage to validate and improve on your design till you think you're ready. This is like the prototyping, also for new standards, being like 5G, 6G. And once you're happy with that, you say like, let's make a prototype and turn this into hardware. And there are like two parts. So one part you can say like, okay, I simulate the hardware, go back to the flow graph, or I say like, maybe some parts I don't need hardware for. It's perfectly fine that I keep it in software, because there's a level of certain things are better to be done in hardware, certain things are better to be done in software. For example, this bunch reconstruction, doing Fourier transform and reverse software is much better than doing this in hardware. Also because of calibrations. And you say like you're happy with your prototype, and then comes the next big step, because your boss wants to use this like 100 times, or he wants to use it operational 24/7. Let's put it out on this fully integrated board. And this is the part where we presently hit sometimes like a roadblock in many industries, and nobody likes to talk about it. It's a bit like this, everybody likes to talk about success, but nobody about failures and about reimplementation. Many of the industries and many people we talked about it, whenever you transfer a prototype into real operation, also like in the software part, people say like, let's keep the concept and re-implement everything from scratch, because we can't use the existing code base because of licensing or compatibility, or it's too heavy, it doesn't fit on a microcontroller or an FPGA.
So basically people keep the concept but basically redesign the whole software stack for their operational deployment. In many cases, some people use also GNU Radio and satellites, but many people we discussed, there are many also that redesigned it. And on the software side for GNU Radio, one of our goals was to remove these barriers through either improved buffers, that data types, so that we can both transmit unstructured and structured data, and to allow also like notably like low latency handling and merge API, which basically is the equivalent of getting rid of those connectors, which are expensive, and to make a more efficient use of CPUs, GPUs, TPUs, and so on. This is not a new idea. I mean, like now, around GNU Radio started around 2000, and I looked at what was actually the first thing that ever used flow graphs, because I thought like, okay, many people asked me, it's like, doesn't this awfully look like, depending on where your engineering background is, like either LabVIEW, because LabVIEW uses also graphical programming, or doesn't it look like Simulink or others? And then I thought like, okay, who was first? And who do you think was first? Simulink. Simulink is like MATLAB and MathWorks, like these two big companies competing. Who was first? Who do you think? MathWorks, MATLAB, Simulink? Who says like Simulink was first? Who thinks LabVIEW was first? National Instrument. Okay, and the others are all undecided because I think it's a trick question. I'm not good in poker. You're right. You know the guy who invented the telephone, Graham Bell? He founded the Bell Laboratories, AT&T, Lucent, Lucent, Comtel, I think now Vodafone. So this was like invented way earlier, already in the 1960s, and they called it BLODI, like a block diagram, where you can see they had already a flow diagram in the early 60s, and if you look a bit closer here, they didn't use the new GRC YAML model for describing flow graphs, but if you squint a bit, you see like, that's pretty much what we're doing today. Why did they do it? They said like, because they built hardware, purpose-built modems and other chips, and this like, before we make very complicated digital communication systems where we spend millions on building ASICs, let's try it first in software, see whether it works. Then we can cast the filters and then we build it. So they used it a long time to just simulate this loop. And I thought like, and even sometimes in near real time. I thought like, okay, there's nothing new under the sun. So let's see what we can learn out of it. And there were some iterations in Bell Lab, it's also continued being used. And then some guys somewhere in California, I think, if you're Berkeley, somebody said like, oh, that's useful. They read this paper and said like, could we extend it, maybe also low level, let's do this for circuit simulations. And they called it SPICE. So then 1973 was SPICE. And then you have Simulink in 1984 and 1986, nearly parallel. You had both Simulink and LabVIEW, which basically followed the same concept. And then later in the 90s, the Germans, like Siemens, they also said like, how do you do like PLC programming? If you ever heard what Semantic S7 graph or PLC programming, they used it in the 90s. And also redesigned their whole processing framework on their whole graphical representation. So I didn't show like all the different ways. So there is something to it, because they say like, yep.
I was going to say there was also the step done at Berkeley around Copernicus project, which had a bunch of different graph-based systems also.
Yep. So it was very popular, and then I started thinking like, if you go back and say like, why do people use graphs? Because they say like, this is the best of both worlds. So you don't get lost in the details. You have like some people who know how to implement the nitty-gritty detail of doing correct simulations, correct data processing. And then people who say like, I have an idea of the domain logic about the physics, what I actually want to do, who don't care about how it's implemented on the underlying hardware. But they say like, I have my signal A that needs to be transformed from A to B. Here I have a feedback loop, and does it still work? We're making prototypes. And this was extremely successful. And then GNU Radio, I think the main and the very important contribution from GNU Radio is publicly funded. And this added like this open source aspect to this, because all of the other ones, I mean, except of BLODI and SPICE, I mean, like SPICE was also like proprietary, but only became recently open source. They said like, if you want to use it, you have to buy our software, you have to pay licenses. It's very limited, you can't extend it, you can modify it. If there's a bug, you have to go in this. And GNU Radio opened it
being open for everybody to inspect, modify, so this true, free, open source spirit, and is vendor neutral. I think that's one of the big power, that it's not biased towards one particular architecture platform, but can be adapted to many use cases. Now you might think it's out-fashioned, but if you look, even like modern developments from Microsoft, Unreal, also game engines, they use the same concept still in large AAA game development and other systems, because they say, like, if you develop a project for if you just have like a project that you can develop with one developer, it's easy. He just hacks down the code that it needs. If you have 2 or 3, if you find like-minded people, they can still work together. But if you make a very big product or system, you have people with a detailed software development experience and people with a very high, let's say, artistic, physics, graphic design point of view. But still, all of them have to interact with each other and communicate. And this flow graphs is an exceptional tool for making complex things and dependencies simple. And yeah, now for us, we're just doing an iteration, taking the same concept and putting it on steroids, better performance, sleeker designs, and yeah, making it, we hope that this will help to make it a bit more liberal in terms of yeah, the LGPL, to make a library adoption a bit also more useful for industry and public infrastructure. So this is like why graph-based signal processing. Now you will also like, okay, I know about this. Just reflect a bit back. Now I'll go a bit on the stack further deeper down. So what were the goals, open source and the communities? I mean, GNU Radio 4, because we're allowed to do breaking changes. We try to make a reimagine or redesign which preserves the clean and lean structure and then has like a modern C++ approach. And also we want to favor composition over inheritance. What I mean by that is normally if you have a traditional prescriptive framework, you have like a framework house where you have certain blocks. You can exchange them, but all of the blocks still have the interfaces the same change, and you maybe just can exchange the colors of your block. But it's not really flexible because it still prescribes you, these are the interfaces and you can replace this block, but if you replace it, it has to look like this, exactly like this, and nothing else. And we went for the route, more like a modular, library-based approach, a bit like Lego bricks. I think like flow graphs, everybody knows Lego bricks. I hope like you all have the fortunate childhood to play around this. Where you say like you have certain interfaces like the small nubs, that they're interconnecting, but other than that, the blocks are completely free. They can have any shape, any form, any color, and you can composite and also use only what you pay, what you need. In this C++ mantra, you say like you only pay for what you use. You can opt, I don't like this block, I don't need it, throw it away, you don't have to use it, and can take a block from somebody else. So what is the anatomy of a block? And it's like, oh my God, you will be thinking like, I've seen this hundreds of times. But I think this was an important exercise that we had in the GNU Radio architecture group. I think lots of the work was also stemmed and coordinated by Josh, who basically went back and said, like, what are actually the important things that we want to preserve? What is important? And what are the pain points? And yeah, for the block, we said, like, the block is basically a pure stateful signal data processing function. You can have a setting expressed as class members or map type informations. And the block has to ensure that if you get certain data in, out, that the constraints are met so that the function can compute this input-output. Then you have a certain inputs, which we call now like streaming input ports. Which is a bit different to GNU Radio 3, they're always synchronous with the type T, which can be either a fundamental, like before, like integers, floats, and so on, or there can be structured data, which is new. So there can be structs like vectors, classes, or any arbitrary object that you might think about it. And the framework allows you to propagate this without any constraints other than the object has to be movable and copyable. Then the second thing is we added tags, and this is also nothing new. Basically, each of the samples or structures and messages can be added with a tag, where you can add some map type information, triggers, and new settings changes, which is maybe a new thing. If you have, for example, a sample rate, that you change the sample rate in a previous block from n heads to another one, that the sample rate can be propagated through the whole chain until the sync, so that the sync, for example, many of the processing doesn't care about the sample rate, but if you want to display it at the end, it's nice that you know, like, oh, this data was generated by this sample rate, so you can put like a proper y and x axis in terms of time, and you don't have to twiddle around what is the actual sample rate. So a bit more inbuilt safety. And this is mirrored with the streaming port. They're also synchronous, but what I mean by synchronous is that there is no additional delay or best effort, but whenever you get an input, you compute the function rate and then generate an output. But the output doesn't mean that the output has to be necessarily like a one-to-one sampling ratio. You can do decimation, interpolation. You can also do a dynamic ratio relationship between input and output, and including that you don't consume inputs, that you do not produce outputs, or you produce an output without an input. But the thing is, if you do normal data processing, you do this with streaming ports. And they're synchronous. We can flag them that the ratio is not constant, but that's maybe like a different constraint. And then we have message ports. In hindsight, we should have called them control ports, because that's also how they're called in GR3. They're asynchronous. They're executed on a best effort basis. They're normally used for changing settings or transmitting let's say, protocol data or things that need to change on a not a fixed time scale. It can be used, and so on. And lots of work. Josh is a bit shy, but I think he did like a tremendous work with the prototype development and also the other people in the GNU Radio architecture group. Please raise your hand of all people who are participating in the architecture group. So like 1, 2, 3. So that's nearly half. That's one of the reasons why with this workshop we have to grow this group to be more people. But this was like was an important work to reflect upon what is good and what do we need to change. So how we modeled multiple computing domain. This is like via scheduler. So you have a flow graph, a global flow graph, and then you have subflow graphs, which are always assigned a given domain. That can be a CPU scheduler or like a GPU. And then you have basically a sort of an orchestration where you have a master scheduler, which is a bit like a orchestrator, which basically delegates scheduling certain works on either scaling themselves, like a conductor, either scaling the works itself and said like, oh, please execute first sync 3 work, block 2, and so on. Or you can delegate to another scheduler, and then it has like another paradigm of how to schedule the work that needs to be executed. And this can change the priority. How you schedule work can depend on the domain. You can make it different for if you run on a CPU, and a GPU, a microcontroller, or an AI accelerator or a TPU. So why is this useful? Because flow graphs, again, mechanical sympathy. It simplifies onboarding for new contributors to participate and contribute more effectively. Everybody looking at this can understand what the high-level concept you're talking about. Everybody can use then like common tools for very fast aspects like C++, or for plumbing you can use Python, or for the high-level aspects in the UI, for example, you can also use WebAssembly. And then you have basically two types of archetypes of people. One are the, let's say, what we call users, which have dynamic operational challenges, want to commission a facility or design studies or ad hoc prototypes, where they can modify this this graph to the liking. But when you put it in, yep. 40, yeah. The GNU Radio 3, I come back to that, it works completely different. Basically what we did, we, like this inversion from inside outside, before the scheduler was part of each block, most of the functionality, and then we said like, no, we remove everything that is within the block to schedule and make it a global entity. Yep, yeah. That was one of the pain points. You mentioned like when you do like parallel computing or with constraints, that you sometimes had a way to that blocks were competing with each other, and that was known. So we have on the one hand like the people like the racing car drivers who know what they want to win the race and want to solve the problem. But on the other hand, you have like this engineer who keep the car up and run floating. And that is basically also like maybe the definition on the difference why we split it up into tutorials, because the view on this flow graph is quite different if you use this to express a domain concept, if you use it for communication, or if you want to really improve the infrastructure that does the signal processing. So.
How do you plan on implementing RF NOC compatibility in this framework?
I'll come back to that as one last slide, vision of the next two. Short answer beforehand, the vision is to invest more into SICL. I'll come back to that, what it is. So that's the reason why we branched this in two, and the user tutorials are led by Jean-Michel. He also asked me that at the end of this talk that he wanted to have like 5 or 10 minutes to explain a bit what is the difference on what is being shown and explained on the user tutorials. And I think from this slide deck you can see what Alex is talking about in his part. So I'm just highlighting the top level, but this one is not meant to go to the very deep things. This is like then discussed in the different tracks, because for the people who are users, we don't want to bother them with low-level C++ and SIMD, unless they're interested, and vice versa. So this is led by Jean-Michel, and initially I thought like this racing car was a good example, but then I noticed when he sent me this picture, that's not a racing car in the background. So I think we have to change it to something more like this. So having like a low altitude orbit. So basically all the people who attend his tracks are getting those spacesuits and going to be the heroes and save the day. So now letting get into the meat. What did we do? The changes for GNU Radio 3 to 4. And we tried to simplify the C++ user API. If you develop blocks for GNU Radio 3, you know that you had to edit 3-4 blocks, that you needed the mod tool to instantiate the block, write getters, setters. And we thought about is like, can we do it simpler? So, and we decided like, yes, because we said like the scheduling is not part of the block. So this is basically the hello world. This is not slideware, this actually compiles. If you want to write a block, you simply state your block name, you derive it as a CRTP, that is curious recurrent template pattern, which is basically a template which inspects whatever you wrote in here. So, and this does like compile time reflection and adds all the getters, setters automatically during compile time. That works very well, so that means you don't have to write any more code, but the compiler has to work a bit harder, and that's also why I have to apologize why some of the compilation times are a bit more than what you had in GR3, for example. But it's worthwhile, and I'll come back to it later. But if you want to write a block, you just specify an input port, an output port, and here you have a setting. For the time being, you still have to use a macro enable reflection where you announce what needs to be exported. But now the compile time reflection is nearly voted in, so it's very likely that it will become part of the C++ 26 standards. I'm hammering on Matthias every other week, where it's like, and by the way, I'm of the opinion that compile time reflection should become part of the C++ 26 standard. And now more and more people chimed in, and it seems to become a reality. So this is not just a future possibility, hypothesis, but it's like possibility. And then everybody knows mathematical functions, and the simplest thing that you have to do is just implement one function, which is process1, which takes one input sample and produces one output sample. In this case, basically takes the input samples, multiplies it with a scaling factor, returns it, and then that's all. Nothing more, literally. And we thought like you can't do much wrong. The only thing what you can do is like write your implementation factor. So we hope that this style of API should simplify block development. It's also much easier for functional tests because you don't need to build a whole flow graph to make sure whether your processing is correct, but in the end you just need to make sure that your process1 function is implemented correctly. So the unit testing becomes easier. Because it's a const expert interface, there's no virtualization. That is because of the CRTP pattern. The compiler can see a much larger scope of functions. And that allows the compiler to do better optimization and merge some of the blocks already on the compile or functionality in the compile stage. And if you like people writing C in the 90s and you see like, oh my, come on, this is like so inefficient doing like a sample by sample processing, you'll be surprised. I'll come back in a slide later. But it's much easier to also to do like an early error detection because the scope that you have to reason about is very small. And yeah, Alex is going into the detail how to use that. We also added SIMD out of the box. This is basically part of the standard implementation, and where we have some convenience method that will become part of the libc++ that Matthias Kratz provided, and then basically of automatically parallelization over the different instruction sets that your CPU provides. So he's going to talk about this in detail. I can just highlight the top levels. But many people will maybe remember the process, the work functions where you get a certain input stream in and out, which is still possible, where you can get like an array of input samples, an array of output samples, also multiple input outputs if necessary, and then you can still perform iterating through your inputs and outputs over those arrays. However, what I would recommend is, and this is like a talk that Simon and also maybe Alex will talk about, is it's much more efficient to use C++ algorithms and ranges because they have already built-in optimization in the compiler. So if you use these structures, the compiler knows better how to optimize it, and it can optimize better than your handwritten code. And yeah, fun fact, beware of premature optimizations. When I saw the process one, when Matthias introduced that, I said like, come on, this will be horribly slow. And my gut feeling said like, that can't be right. And before you start optimization, before you start using this process bulk function, if it's not necessary from a functional point of view, start with the process one. Because in many, many cases that we tested, the process one function is actually faster. And we have some benchmarks to back that up. And the rationale is because the compiler has a reduced scope that it can better exploit and compile, and it's also more cache efficient because you have a smaller code section that fits better in the L1, L2, and L3 cache. I think I skipped that. Yeah, you have also like a way of automatically documenting the block. So basically the code is single source of truth. So you can add just a small description, and this is later used automatically without any doxygen or any other code annotation to derive documentation how the block is working. And this is like a pre-production code example for an FAIR filter, for example, where you have also like a callback functions like settings change, where you say like, I don't want my settings updated without a validator, or where you have like some other complex dependencies that you want to apply and test before the settings are actually applied to the block. And yeah, self-documented code is single source of truth, and based on that, you can basically generate a printout example without any other tooling, just using C++ templating. Okay, this is like something for people who just use small installation or like a prototyping. You might think like, okay, I have one set of settings and they don't change, and if I need to change them, I stop the flow graph, change the settings, and restart it again. In our case, the systems are running 24/7, and we're not just having one use case, but we have multiple users using the same SDR hardware, so we have to switch rapidly between different modes of operation, producing one iron species, producing uranium, argon, protons, and switching back and forth, but we still need the same pre-processing for all of them, but with different gains, for example, or different filters that are adapted on the given use case. So many of the hardware devices are not exclusive. So then we have like two use cases. One is without feedbacks. So there you can say like, okay, for this use case, you can just operate multiple parallel signal processing pipelines or graphs. But as soon as you have feedbacks, that will not work anymore because you can have only one system that drives the hardware. So you need then to reconfigure the whole feedback loop in an orchestrated manner. And this is particularly important for us. This is like our tube map or subway map, where you can see like you have a Unilexis 18600 HESR, and depending on the modus operandi, it's a bit like Tetris. Each one of them is executing a certain mode of operation and then rapidly needs to switch to another one and back to another one, and yet. So we have a device that looks in the sys18 but needs to be reconfigured every other second and back and forth. So this is, for example, different settings when we accelerate. Jens explained the synchronous nature, that we have to ramp up the magnets while changing at the same time the frequencies, changing gains, and this is like how we model that. This is free of charge. If you don't need it, you don't pay for it. But with this optional multiplex block settings change, you can basically flip between settings, like a good setting, bad settings, on the fly using this context, special context tags. And this allows flexible multi-mission and multi-user operation. How does it look like? You might think like, oh, I need to implement a lot. No, most of the stuff is done implicitly. So basically, if you do a different set, then these settings like scaling factor are exchanged automatically in between the next time you're being invoked. And you can declare like a context variable where you can select, okay, what is, as an info, what is the present context I'm running on if you want to make some special magic based upon that. So this is like a simpler API. Let's talk a bit about performance improvement. One was the log-free buffers. So we all want to improve latency, bandwidth, and throughput. This is just like a small picture to explain the differences, but I guess we're all familiar. Latency is the delay between the cause and the effect. Throughput, the amount of material that goes through. And the bandwidth is maximum rate of data or compute that we can perform. And if we need lower latency, we either have to maximize our I/O bandwidth, or memory bandwidth, or compute efficiency, or we have to minimize the data that has to go through this pipe and compute sections. So concurrent and parallel, basically concurrent is basically that you have different streams of execution, but not necessarily parallel, and parallel basically you interleave with this. And there, it's also like for the latency, it's basically the longest execution that you need, and normally we want to have this as small and deterministic as possible. There's an excellent talk by Jill Teen from Azul, how not to measure latency, that goes a bit more into detail, and I put like a PDF and a video link, YouTube video link on that. Yeah, mechanical sympathy, know your hardware. You all know how, maybe have seen this picture before, this is like how a CPU die looks like. You can see like here highlighted. I mean, it's not really colored. This is like a post-processing. I think the guys from AMD added that because otherwise we would not recognize it. But you have multiple cores, multiple memories. Some are L1, L2, L3 cache. Some are shared. Then you have sometimes multiple dies that communicate across each other. And how you implement the code determines how efficiently you can use this hardware, or whether you have to do certain computations multiple times just because of synchronization and inefficient structures. One of the ideas is like, this is a bit like a, can't go too much into detail, this is a bit like a nutshell. On the lowest level, on the CPU core, you can compute the fastest, but you have very small L1 cache. And then the higher you go, you get more cache, but usually it becomes slower. So the idea, if you program something, you want to make it as cache-friendly as possible. That means make your code sections as small as possible, as optimized as possible, so that everything can happen here in the yellow part. And only go up to the higher levels, complicate your code if necessary. And for this, having template programming and modern C++ and GCC and Clang are key to that. Yeah, there's also like, if you want more detail, there's like a tutorial on this aspect. So why is this important? Because one of the pain neck is like that why we want to just compute samples, that when we switch between the different tasks that we have to execute, there's typically like an overhead. So the old model for GNU Radio 3, each block was also a thread. So whenever you spawn up a thread or you need to start for the thread, you have a context switch that takes a certain amount of time. You have a systematic overhead for checking how much time do I need? Can I actually execute my work functions, or should I just return back to sleep until I get more data? And then if you add these again up to parallel execution, you see like from the original latencies, all these tiny amount of context switches and systematic overheads add up so that your overall latencies become bigger. That's a fundamental limit. So that was one of the way that we try to tackle is how to get rid of these small blocks, because they're now unavoidable. Are they really necessary from a compute point of view, or can we just drop them? And yeah, to give an idea on what the overheads are, some cases it's just like a microseconds, up to 10 microseconds. So this is like for thread switch, context switching. But even like if you go from the caches, we're talking about tens of nanoseconds to 100 nanoseconds. So the question was like, how to get rid of it? Because even if one classic paradigm is, in order to get rid of this overhead, this is Amdahl's law, people's like, don't worry about this.
just call a thread and compute 1 megabyte of data, then the proportion of this context switch and this checking whether you can execute the work function doesn't matter anymore, which is true. In terms of throughput, that's a good, valid approach. They say, like, compute more without interruption, you get a better performance for throughput. But at the same time, if you say, like, I want to compute 1 megabyte of bytes, you have to wait longer, so your latency is larger. So if you need somewhere an answer which comes in a millisecond, this is orthogonal. So in the end, if you want to have short latencies, you have to tackle this. And by tackling also this overheads, your throughput automatically becomes better. So we wrote a new buffer. In the nutshell, it still used this POSIX double-mapped M-mapped buffer that Eric mentioned this morning, where some of the resident C++ experts actually tell me that is possibly, but probably, or very probably, undefined behavior. So we're using a feature which any future GCC version might just remove the carpet underneath your bottom. But it's still the default, but you can also opt for new alloc strategies, and you can see that the difference is not that much anymore. And what we did is, like, we added this possibility of adding tags to minimize that interface. But in addition to the unstructured data types that we already had in GR3, we also added structured data types. And this can be, for example, from John Saleh's PMT map. This is like a polymorphic type map. Or you can use vectors, you can use tag, or we have new data format like packet, tensor, dataset, or whatever other struct you think is useful for your application. So, and with these buffers, there's several ways. You can have a fan out, that's the classic way, but you can also do a fan in, so it's also multi-producer, single receiver, or multi-producer, multi-receiver, or if you want to, you can even pass through when you say, like, I don't need the data, I just want to look at this and I don't want to copy. This we tested just conceptually, but in the end we built it back because we didn't have any real use in-house for that. But you could write a block that makes use out of that. So bottom line, this is like a drag race. It's a very artificial test. This is not like a full workflow test, but just to see, like, what is the throughput, but on the same ground, producing samples in and out. How long does it take? So in red, the red corner, you have GR3.10 with the circular, with the virtual memory buffer, and with the simple one. And on top you have GNU Radio 4, and you can see, like, you have up to a factor 10 improvement. And the main ingredients is because it's a lock-free structure. So whenever you read and write, you don't have to look for a mutex. But if there's no data contention, it's free. So if you once the CPU knows there's nobody else writing on the memory segment that I'm reading, it doesn't kick in the lock and no synchronization of atomics. Lock-free uses atomic compare and swap paradigm. This is like for the C++ experts. And by having strict typing and const expert functionalities, the compiler was actually able to optimize larger structures of the code and remove the virtual interfaces, which got rid of some of the overhead of the existing implementation. But if you don't like it, write a better one. You can exchange it. It's modular. It's not contractual. This is now the performance. If you look at how many producers against how many consumers. In blue is the new lock-free structure. We can have an interrupt service routine rate of about 30 megasamples, or 30 million interrupts per second to handle in the simplest case. But you can see, especially for many consumers, that the lock-free buffer outperforms it by order of magnitudes here. And only when you get into the range where the readers actually have to wait on the writers to produce data, you can see that they both approach asymptotically the limit of the number of cores. So you can see, like, a small diagonal line. That is where not enough threads are available to compute. New data structures. I'm not going too much into detail. Maybe Alex is hinting at it. But before you could only transmit fundamentals, but now you can say, like, this struct, your buffer contains this data set. And then we made, like, different subset. A packet, which is just contains a timestamp, some data, and some meta information, can be stripped. Or you have a tensor, which has also a bit information on. A tensor is like a fancy mathematical way to express vectors, matrices, cube, volumetric data, and so on.
or you can have a data set which is very similar to the HEP, high energy physics equivalent of event processing, where you have also lots of other heterogeneous data being stored and meta information. You had a question? Oh, no. Okay. So why do we need it here also specifically at FAIR, GSI FAIR? So having a continuous stream of data is normal. Then we annotate it with tags, with context information, or like some trigger where we found like, oh, this sample is interesting because we found an edge, transient, or something like else. Can apply it to an FFT, then this FFT can produce a vector, and then group it alongside this tag, and then, for example, transient detector can filter out only the vectors that have actual triggers, and then you can process it further and put it into storage data and analyze it. And this concept is similar to the old PDU concept, but with the difference is that you can put in any data type. Like you don't have to mimic, say like, okay, this range of bytes is my vector data, but you can put actual vector data or packet data in there. Or you can group them and add additional meta information, then it's basically your data set. Or what you can also do is that you do a context matcher that is like, please give me, I have continuous streaming processing, but I'm just interested in certain parts of your transmission between the start and stop, and you can put markers there, and then I have a matcher filter that basically extract on this context only certain subparts of your data, and then propagate them as data sets into a sink. And then you have different ways multiplexed with start-stop, just with context 1, or if you just look on the transient, or you do just continuous monitoring, and so on. And this way you can build like very complex flow graphs. Maybe my microphone is not. Okay. Can still hear me online? Yeah, maybe. Where you can do also like more complex operations, not just on samples, but on those data sets, on this high-level mathematical objects, and do transient detection there. And because we are not, we changed the way how buffers and how the schedule works, we can also now support feedback loops, so that you can say like, please compare my new sample against the sample that I had previously. So here the main takeaways is now we can also use to process structured event type data, like packets, data sets, or like HEP style events, support feedback loops, and we have context dependent settings that you can get around. And this is also like a scheme. I mean, like this concept is not very new. You have this also like in other domains. And the idea is that we build up now an ecosystem with also high-level functions and flesh out these blocks that we can make these control loops work, similar to other known graph processing tools, tool chains. So SIMD, this is like a very extensive subject. And please forgive me if I have to gloss over. I think Matthias is, or Dr. Kretz, I said a doctor only for people who really deserve it, and he made his PhD on that topic, so he deserves this for sure. Has a very detailed talk on this. So I can glance just a bit over of the features, but an important thing is because we removed virtual inheritance and moved to strict typing and templating concept like the CRTP, we've been able to allow the compiler to do much larger section of code optimization. And here's like let's say a structure where you have a base class where the other derived class inherit virtually. And you can see here that every virtual interface creates basically a barrier that the compiler can't inspect, because it has to assume, yes, we share all the same base class, but your implementation, you might exchange it during runtime. And the compiler can't know that. So it says like, whatever is virtual, I can't go beyond that boundaries. That is, let's say, good in terms of compile time performance, because you have your small section. It has to worry only about 10 lines of code. But if this 10 lines of code is executed 100 or 10,000 times, it can't see this recurring loop and not optimize for it. And that's this overhead that you have in processing, and processing also over this bulk, previously over this sample-by-sample interface. Now with this CRTP concept that we added, this is basically in a nutshell how it works. The compiler can see through and say like, I'm not stupid. All what is basically the functionally is the same left and here, but the compiler sees through and says like, come on, you don't do anything. I just return 1. Why do you trouble me with this? And that's what we want, because if you have dead code or things that are the best computation or the best signal processing is the signal processing that you don't have to do. or the best buffer is the buffer that you don't need. So what is the best buffer performance? The best buffer performance is when there's no buffer required. So one of the advancements that also Matthias introduced was like this merge block API, where basically like, let's get rid of the buffers and the ports, just glue them together, and then just say like, okay, I have an input buffer, and then I compute block 1, 2, and then the sync in one go, and then the compiler can optimize over these 3 functions and get a much better performance out. So this, this is optional. You don't have to do it, but if you see that a certain functionality is recurring or is very minute, you can merge it together. This omits the buffer and facilitates a larger scope of compiler optimizations. Also reduces the memory footprint, and that's more efficient use of the different caches, smaller code sizes, and which is also important because code size is also kept in the cache. So less code, the faster it run. And yeah, the target, and we have some proof of concept that we're able to run on a microprocessor, for example, on a Raspberry Pi 2040, that's the Pico. So we're talking here about microprocessors that only have 2 megabyte of flash. So that's the limit that we got. We have to work a bit on the user experience, because if you're in a microcontroller, there are lots of other constraints. You don't want to do printouts, because most microcontrollers, for some reason, don't have a console, or they don't have threading even. So in the proof of concept, I had to manually disable the threads and the printouts, but we want to make it automatic. When you target for microcontroller, that only the absolute minimum is compiled in. And yeah, we hope that this facilitates an easier transition from a flexible R&D prototyping into production use. So SIMD, like we all know, basically we have a certain set of instructions and certain data, and then we have like some magic that does some mathematical performance operations on the instruction data sets, and then you get one result. And then you can streamline, rinse and repeat, but most CPUs, to get faster, they can't increase the clock speed anymore, because that's the thermal limit they will reach, so most of them clock out at 5 gigahertz and only for short times. But the strategy that was in now for the last 14 years is to go parallel. So basically SIMD, where you have multiple data, you have the same operation, but you say like, let's execute this on a larger chunk of data and then get all the data out. And this is still executed in the same clock cycle. So when you had like 1 instructions per clock cycle, then now you can have like up to 4 instructions within the same clock cycles, and that gives a factor 4 views. And if you don't use that, basically your performance is as slow as Python. So you have to interpret every assembler code one at a time. And if you want to be fast, you have to use this vectorization. I mean, there's some libraries like Valk, for example, that did already some kernels that optimized this, but this is now more and more streamlined to become part of the C++ standard, so where it will not work just for one architecture, but for any architecture that the compiler is being designed for. And I think that's a very powerful tool, and that's an aspect that Matthias is going to talk about. Now, how does it work? Okay, I'm not reading through this. But there's a big shout out to Matthias, who adopted us a bit and said like a very nice guinea pig, and who drives this also at the ISO C++ committee as a subgroup group 6 numerics chair. But you can see, for example, if you have here's a bunch, it's a benchmark from simple flow graphs. So from a source to sync, source, a copy, sync, source, with a constrained number of samples. And then some processing, which have certain limitations on how many samples they can consume or produce, up to something like multiply by 2, divide by 2, and then add -1, where you would normally say like, okay, times 2, divide 2 is stupid. That should cost, I shouldn't waste any CPU cycles on that. And then to make it even worse, we said like, okay, let's do this 10 times, just to accentuate that I have many long chains of simple operation. And then you have one, let's say the runtime performance, which is like about 80 megasamples per second, so it's still performing well because of the new buffers. But if you merge it, you get to 250 megasamples for free. So that is significantly faster. And for the other optimizations, we get even up to the realm of a few gigasamples per second that we can compute on the CPU. This is just compute. Don't mistake this that you can now do when you read like 5 gigasamples, I can do my 5 gigahertz. I don't need an FPGA or DSP anymore. You still need the data out from the device into your RAM. So this is basically performance when most of the data is kept nearly always in the L1 or L3 cache. But what you also can see here is the same times 2 divided by 2 and minus 1, once with the process 1 implementation, one with the process bulk. And we made it fair and made the best optimization that we can do. And what you can see is, the box is unfortunately a bit misaligned. You can see that the process 1 is significantly faster than the process bulk. For me, that was something I had to swallow along because I was used for decades to write low-level C++ system code, even to write assembler code and machine code, and I thought like nobody can beat my assembler. I knew nobody could beat my assembler. I stopped in 2006 because GCC produced same quality of output in 10 minutes, what I needed like 3 months to write. So I stopped writing assembler in the mid-2000s. But for that manual loop unrolling and those tricks that we all as C or C++ developers are used to use, when I saw this, oh, this is not true anymore, that took some time to unlearn. To say like, okay, this is a habit that I acquired over 20, 30 years. It's like, that's not true anymore. Because compilers, especially for larger code bases, they're way smarter and can see much larger scope of algorithmic complexity than humans can do. They can see also potential optimization that we haven't thought about it, that by reordering, because C++ or C, any modern CPU, doesn't execute code sequentially anymore, but is also allowed to execute out of order. This has to do for performance reason, and many of this out of order execution make the actual code that the CPU runs look much different to what you think you're writing. Bottom line is, avoid premature optimization. First write a code that is logically, algorithmically clean. So if you can cut down a numeric complexity from O(n) cubed to O(n), that's a much bigger gain than you get by this micro-optimization in C++. And this, I will talk about this more in the last tutorial in the programmer's track. So yeah, let's talk a bit about timing. This is like this 2 o'clock problem. How to synchronize about multiple nodes. Particular at GSI FAIR, we have a massive multiple input, multiple output signals, and normally if you want to synchronize them, you're trying to keep every receive channel on the same data acquisition board. So if they all run on the same board clock in the same ADC, or the same set of ADC that run on the same clock, that's the best way to synchronize it. However, this is not always possible. For example, at FAIR, we have some systems that are distributed over 4.5 kilometers, so we can't pull cables and keep the signal fidelity over 4.5 kilometers. But also, we have a channel count in the order of, the raw channels in the order of 3,000 to 4,000 signals. So there is no duck with 4,000 input signals that can sample at 200 megasamples per second. So you have to synchronize it somehow. And this is like this 2 o'clock problem that Eric mentioned. Yeah, how do you do that? Maybe Simon implemented it now. Basically, the idea is that we made a inbuilt integration for timing synchronization. The main thing is that we use tags to synchronize data streams. So we abstracted the timing synchronization through a generic block, which could be white rabbit timing receiver, could be a GPS receiver, or if your slow timing is enough, via UDP timing receiver that sends out synchronization methods, or has a hardware link to your actual digitizer, and then basically it adds a tag to the data stream, and with this meta information that comes through, it says even like that's the pulse per second, or the UTC time, or whatever other information you want to put on it. And if you do this across multiple nodes with the same timing source, for example, white rabbit, then you get data streams depending on when you start the node. You get earlier data or later data, but you have a unique alignment. So this circular buffer has to align, so this comes at the cost of latency. And so it's like I hold the data until I have 2 matching tags. And then I can count back and say like, okay, I can emit the data. And then you have to handle with the corner cases. If one clock is slightly faster than the others, you have to choose what do you do. Do you interpolate? Physicists hate interpolating data, so because it's fake, we don't make up data, so we drop the channel that has too many samples. And yeah, Simon did a very nice implementation handling all those corner cases so that after the synchronization block, you are sure that the rest of the flow graph is executing synchronously. And the synchronization also works not just on the receiving end, but also on the sending end. And yeah, this is solved through standardizing the tag through default tag names like trigger name, trigger time, trigger offset. So now, let's say maybe the biggest thing that we changed, this is the most important things why Josh and others started this big 4.0 revamping was like to rework the schedule to make it a bit more flexible and to address certain pain points. So the two limiting factors in the GR3 design, these were mainly let's say call them the main pain points and reason why GR4 development was started, is all blocks are also threads, and their processing function is ultimately managed by the system scheduler. So that is basically by the same OS scheduler that runs your graphics card or your other blocks. And on that level, all the GNU Radio blocks compete basically with each other and also system tasks for the resources, for the computing resources. And then you can have issues with starvation, non-determinism, or other blocks that are not non-embedded or microprocessor friendly. And also a lot of the latency is defined by the maximum minimum buffer data intake is not globally controlled by default. So basically the latency is defined by how many blocks and how many buffer sizes you have in the input. And this creates undesired latencies and also a larger memory footprint than needed. So how does it work? This is like a simplified flow graph. Just ignore the constraints on the bottom for the moment. If you have a source, block 1, block 2, block 3, and sync, let's assume that the processing function takes the same time for all of these blocks. If you want to have some samples in the sync, you execute source 1. It fills up the buffer to the brink until it says like, hey, I can't execute anymore. Then you would inform the buffer, hey, I have data. Then the block 1 is woken up. It always takes the same data, and depending on how big the data is and how much the buffer is, it propagates it through, and then you get like a accumulating larger chunk of data where basically the smallest buffer in the chain will, actually it's a combination, will determine what the latency is until you get a sync. Now if you add certain constraints, and it's like, hey, my source produces only 1024 samples, my block 1 cannot consume more than 128, block 2 can only produce 1024 at a time, and block 3 is like, well, either 32 or up to 128, I take whatever in between. And the sync questions like how many samples will arrive there. So let's play a game and let's see how this would play out in a scheduler. I simplified it a bit. I ignored the contribution from the source. And so like the source is executing, has an overhead because of the context switch, checking, am I allowed to run? So like, yes, and I produce data that's with a solid thing. And then it says like, let's call block 1. And because I produced 1024 samples, and I can execute 120, I can consume 128 samples, it says like, yes, it's okay, I can produce 128 samples. But now the problem starts, because if I go to block 2, it's like, nah, I need 1024, and you just gave me 128, go back. And it goes back to sleep. So block 1 goes back and says like, okay, I have still buffer in the input, let's consume the next 128, goes back to, block says like, now can't do, block 1, block 2, goes back and forth until you get like this 8 time through. And then basically block 2 could produce data, but because it acknowledged, it also notifies the sender and says like, hey, I got data, do you have more? But block 1 says like, no data, so you still execute the block 1 without actually having a chance to produce data. Now the same thing happens with block 3. You go block 3, sync, and then you go through. And if you count, that's basically the sequence. That's the earliest time that the sync actually gets samples. So if you look on the earliest day you get data, you have a latency of 19 cycles, plus all these overhead. Do you think this can be done better? If you look at the scheduling task, you're just one guy, how would you execute it? you would probably say like, let's produce the data, and then I know this block can't work until it has 1024 samples. Then let's execute block 1 8 times, and only then execute block 2. And then the same, execute block 3 8 times, and then sync. And then you have basically the most efficient way how to execute it. And that's basically the ideal sample. And then you have basically the throughput is optimized. You have much shorter chain, much quicker to your result, and even the latency got lower. It's not much by 1 cycle, so you get your data 1 cycle earlier. However, if you say like, I want to get earlier data, then you can say like, okay, the first time this block 3 produces data, I go to the sink, then you add it here, and then if you say, I take the same flow graph, but I want to optimize it for latency, I get my first data, my first sample out already in 11 cycles. And that is an information that GNU Radio 3 had a hard time to optimize for, because each of the block didn't have a knowledge on what were the constraints from the previous block or the blocks behind. There was, I mean, like by default, there was a very interesting talk by Matt Ettis, like at the GRCon 2019, where he talked about this issue. I mean, like, this is not, I'm not telling something new. I mean, like, all the in-depth people know about this. And they say, like, also, like, what can you do? You can shrink the buffers, and there's several ways how to do it and how not to do it. Even he said, like, for as GR3 has worked, you shouldn't do this because of certain caveats. But what he and Derek implemented this, proposed is basically, let's put like a gatekeeper. So you have your chain, you have your data, your vector source. You send your data out through a long chain, and then you see, you inject a tag, and you see like how long does it take until the tag arrives at this final block. And only once this block receives the data, it sends a message to the gatekeeper in the beginning, so like, okay, now you're allowed to produce more samples. That works, but still has this problem with the overhead that you need to ping each of the blocks. So you have this ping back and forth for each of the blocks. But it is a way to control latencies. It's a valid solution, but it's on the user level. So if you want to schedule this for different sub-topologies in your graph, the flow graphs become very messy. And what we did is basically the scheduler does the same approach, but implements it not as a block, but as a semi-global schedule, like a orchestrator or a conductor. That says like, okay, I know about the topologies. I inject the knowledge of the constraints which I can inject in while the flow graph is being constructed, and I can ask to make this to take the topology into account. So basically, it's just an inversion. We moved all the scheduling information largely out of the block and into a global scheduler that basically orchestrates which block is executed in which order. And the importance is also like the optimization that we could do there, because in the end of the day, if you have 1,000 blocks, but only 4 cores, you can't execute 1,000 blocks at the same time. But you have only 4 cores, you can only execute 4 cores at a time. So by using threads, you have an unnecessary overhead of putting the thread into a core, getting out, in, out, and then you lose performance. But if you know that you have only 4, you can say like, let's keep just the processing function in my global shared queue, and then dispatch it to whatever core is available. You can have either a global queue or local queue, and can basically optimize it on that level. And that is most efficient because it minimizes this context switches and also the need for triggering the branch in terms of branch prediction, the false branches where it's like I call a block even though I know the block will say like, no, sorry, I can't work with this, it's not enough data. Yeah, we still need to be mindful that we need a distinct scheduler, for example, for the CPU. There you have like a default, fair, real-time, or one. Typically here you prefer smaller data chunk sizes to process because you want to keep the data within the cache and also to optimize the SIMD performance. But for the GPU, for example, if we need to transfer data to the GPU, the data transfer is very heavy. You don't want to do sample by sample, but you want to do larger block size. And that's the reason why the GPU has to take more data in. And then for each of the domain, be it CPU or, for example, in this case, GPU, you can implement different scheduling choices. For example, you can choose a global versus per thread or core work schedule queue. You can use CPU shielding or schedule scheduling and all the other different techniques. Now what we did is, just to illustrate for argument's sake, we're not going through all the cases, but here in the top we had like the simple flow graph, which is, I put like a imp and an angel, because these topology were specifically designed to trip schedulers, which are hard to solve with the existing scheduler, but where we wanted to put it out as a challenge. So the question is like, what is the correct, best, and most efficient execution order? The thing is, I can't tell you that is the best scheduler for all applications, because there is no single one-fits-all solution. So we proposed like a certain set of topologies, like blocks with parallel branches, blocks with feedback loops, blocks with multiple outputs where you can check on how do you optimize the latency from the source to the sink, or throughput, or doing this type of structures, which look a bit weird, because I mean, for GNU Radio, most people are not used to seeing feedback loops, but this is a very common topologies for neural networks, where basically, or recurrent neural networks, where part of the output information is put back into the input, and we apply inference or model learning. So what we did is, just as a proof of not concept, it's like a default implementation, but just to show what is possible, we have like 3 scheduling policies. One is like busy looping, depth first and breadth first, where basically you get to different strategies how you traverse the flow graph. But there are many other possible solutions, like topological sort, critical path method. There's a whole region or a whole area of research, active research being done. And you can have a look at the README to see through the list. And people can have a look at it and see like what is actually best. We don't know what is the best topologies, but one of the next step is to start now with the API, to start like a sort of a GNU Radio competition to find the best default scheduler that's good for the vast majority of users, the best real-time scheduler that optimizes for latencies, the best throughput, and then you have like a friendly competition who can write the best scheduler, for example, for this set of topologies that we have outlined before, and then benchmark it, and then see like who wrote the best version, makes it as the next, like a patent, like the next GNU Radio 4.0 scheduler in. In any case, this is modular. If you don't like a scheduler policy, that can be exchanged. So it's like, nah, I still use my own. The level of getting into it is fairly low, but it's technical. That's the reasons why we said like we needed a dedicated developer track, because it's not all scheduling aspects are for the faint-hearted, unfortunately. So what is next step? I mean, like there's several domains like community engagement and advocacy. This is very important. I mean, like as much as this is about technology, it's also about people. I mean, like if you have a team of 1, you're always in agreement. You have the best and worst ideas at the same time, but as soon as you have a large group of people, we have to find support and share ideas and also reach a common goal. And so part of it is fostering the community, but also to increase the visibility, because the more it's being used, also being publicly used or visible used, the more the funding agencies are likely to say like, yes, that's a cool project, we fund this. Part is also like to educate and document. I mean, like, it's not just software developer that we need, but we need also educators and people who like technical documentation, because now for the people in the know, everything is clear, but we realize that somebody who enters the game late has a harder, steeper learning curve, and we need to get this down. And in the country of the blind, the one-eyed is king, so we need like the people who have a fresh perspective and say like, okay, how can I explain it more adequately to somebody who has never seen this concept? And then the other part, what we do during this workshop is continue on the core library, but also improve the user experiences. That's part of this workshop. And we implemented a certain set of minimum functions to use already GNU Radio, which is largely okay for our purposes at GSI FAIR. But we are, for example, not digital communication experts, nor do we try to attempt to. This is the part, if this is needed, that others with that specific domain knowledge should jump in and add their contribution to that. Also, we would like to enhance the user experience. also for non-expert users, and we want to make it as widely accessible via GCC, Clang, and mscripten. And while I think, like Eric once mentioned, is like GNU Radio didn't start out with the UI. So for the people who just want to do signal processing, they're happy with their Python and their C++ script. But I think it's also fair to acknowledge that GNU Radio Companion made a big, big impact on the community and widened the audience of people who can use and interact with that. We should also look into develop an intuitive default UI to simplify the user engagement with the new GNU Radio 4.0. We have an in-house development for UI, which is suitable for our purposes, but this, which can rehash and people can take code or steal or take this with no issue. But this code we can't. That's outside of our scope. We can't stem a UI for the whole world. So there's somebody who knows the other domains better, who should provide either an integration into GNU Radio Companion or make a new UI. And there's some long-term performance visions. One is to invest more into SYCL. This is integration of both FPGAs and GPUs. One of the targeted compilers is adaptive CPP because it's streamlined. It doesn't make a difference whether you run on the CPU, GPU, or an FPGA. Invest also more into developing on microcontrollers like Arduino, because it's a nice, neat tool for educators to say like, hey, that's my Arduino, and you can run a GNU Radio flow graph on it. Why not? And yeah, we need to expand the core team to increase the bus factor by, that's a proposal by involving industry, public labs, and academia, and foster the cross collaboration between different teams. One thing, last but certainly not least, if you want, maybe you all heard about the new White House directive, but this also for the Europeans. There's a new cybersecurity directive in the EU. We have to become more and more compliant with those rules and regulations. And so we have to look into security hardening. That's also the reasons why I think it's important to engage with industry and public labs, because the same requirements that are coming for all NSF or DOE or Helmholtz-funded labs will also come for the industry. So we have to collaborate on that. That's all. I forgot my blue overall, but I say like thank you. And there's like a quick overview on what's happening on GNU Radio 4.0. And I'm looking forward to a technical dialogue. Any questions?
Is this smoking? Okay. I've got several questions. First of all, the concepts of feedback loops and several connectors pointing into one block is new, but how is this behavior defined? Like, if I have multiple signal sources pointing into one processing block, what is happening in the buffer? Is it just a jumbled mess of data, or is there like a...
The thing is, if you traverse this part of graph theory, because you're part of that's the reason why graphs are very powerful tools. While traversing the graph, you can see which blocks you already visited and which port is already visited. So when you see, like now, you have a check in GR3 that you have a loop detected. It's the same algorithm that detects a loop, but instead of saying like, please go away, I can't handle that, we say like, okay, there's a feedback loop and we can calculate what is the latency that you accumulated through the block. And then you prime the input buffer with the default value with the number of latencies that you accumulated. For example, you accumulated 10 samples latency while going through. Then while connecting that port, you select, oh, this path getting here, 10 samples latencies, prime it, so then when the flow graph starts, it has already 10 pre-initialized values on this input and can continue calculating.
Does the user do this or the scheduler? Does the user do this or the scheduler?
That's that has to be fleshed out more specifically, but it's between the scheduler and graph, actually. But it's mostly scheduler. Because the scheduler traverses the graph.
And there was several slides earlier, there were like multiple arrows pointing into one single port.
No, that's for the buffer. That's different. Oops.
Yeah,
You mean this one? This multiple producer, multiple input is mainly for the message boards where you send in one sample. So that's a trivial way how to make feedbacks.
Okay. Next question I have is, you once described the merging of several blocks into one. Is this just possible at compile time, or does this also work from a graph?
We've implemented now for the compile time. We haven't implemented this, but there's also a light version during runtime, but where you can skip the buffers, but you still have the overhead of looping through each of the functions. But most of this is the best performance you get during compile time. That's also reasons why I think it's favorable to look into adaptive CPP, because this is basically just-in-time compiler. Mm-hmm. So you could say, like, give me my flow graph, and then without having to recompile the whole program, you can say, like, take this flow graph and then recompile it just in time. There are two paths how to go for it. Either using adaptive CPP, which is like an additional dependency, is basically like a Clang LLVM-based dependency that would be available and for the runtimes that can support a compiler, or to spin up a parallel compiler that merges the block and then injects the code during runtime using DLOpen, which sounds dangerous, and it is. That's the reason, like, which we have to see which path we should take. I mean, like, adaptive CPP, in my view, is more modern and the cleaner approach, but the other way is like dynamic code time injection, runtime code injection, where the compilation time is, you start off with the unoptimized code, spin up the graph in a compiler, and once the compiler says, like, I'm done, you replace the old graph with a new merged one. Okay. But it's mostly now compile time.
My last question is about the current YAML files. How will they get replaced, or will the YAML files stay? Will they become comments, decorators? What happens to them?
We're trying to keep the definition as close or actually identical as possible as the GRC. So the structure will be the same. However, the block names may change. So, I mean, in terms of syntax, it will be the same, but the block library may have different names because of the templating. A block that handles floats, a block other than the same processing function that handles float, doubles, or others will be named differently because how they're generated in the back end. Maybe we can there's a way of how to do a translator between GR3 blocks and GR4 blocks. But this is something that we have to discuss upon. What is the better approach on that?
As a block developer, the YAML files stay to, like, indicate what's happening in the companion then? The YAML files stay as like a separate file when I want to develop new blocks for GNU 4.
Yeah, I mean, you can use them the same format.
Okay.
And this is high level. We mostly, at GSI and FAIR, we mostly worked on the low level part. And then the agreement was like everything that is in the larger ecosystem, where we just very quickly opinionated. We said, like, let's say, for example, UI. We said, like, we can't take a stand, and that has to be handled by somebody else. I mean, we know that it's possible. We can wrap everything in Python. We made a strong simplification. I mean, also a big shout out to John Saleh, who made this PMT implementation, because that's the bottom line. So we limited our public API to only PMTs, and that simplified the Python interface because we just need wrappers around the PMT and a few handful of 5, at most 10 functions, and then the whole code base is Python pluggable. But also this Python integration, we made a block where you can execute Python code within the block, but this stringing together using Python, that's something where somebody can rise to the occasion, say, like, yes, I flesh it out and make a good Python integration. I played a bit around with CPython, and I find it a bit too scary, to be frank. I know too much about CPython now that I would not be qualified to do this Python integration because I wouldn't be able to sleep in the night. But if somebody else feels more better and has a better idea how to make it smart, please.
There was a question on the YouTube channel about the build time of unit tests.
Yes.
If there's anything we can do about that.
Yes, that's one of the open pain points of GNU Radio 4, because we got rid of the virtual interface that allowed us to be much more runtime efficient, because the compiler can see a larger scope of code that it can optimize. But the problem is that the larger scope also means that the memory footprint during compilation becomes larger. So if you have some compilation units get up to 5 gigabytes of RAM during compilation, and for silly reasons, you try all different possible permutations and see like which one is the fastest. And out of the 100 permutations that computers select, only these two are useful, and it drops all the other ones. We're trying to see how we can further optimize on the templating structure that we use, and we're looking forward to people who have an idea how to make it more efficient without compromising computation performance. But also with Matthias we discussed it, meaning the mere fact that LLVM produces the same or sometimes even faster code than GCC in less than half the time, for me points out this is a compiler bug. I mean, like, not that it does produce incorrect code, but if a compiler takes a factor 2 more time for not even faster code, I say like, please. But yeah, I don't know what is the best leverage to, because in the end, the GCC, like GNU Radio, is an open source community where people contribute. There are only a few people who are actually hired to improve compilers. And the question is like how to engage and how to help them to make it faster. I mean, I looked a bit into the GCC code. I was scared that our template names, that some of the optimizations are based on string comparison. So you have functions and they do permutations with using strings. And I was thinking like, if you have a type that is only 4 bytes long, like int, float, no worries. But sometimes this templating type, if you have additional attributes, can have up to 1,000 long type names. And then you have to think about, for all the different permutations, it generates this 1,000 times 1,000, you get very large code structures, and that just takes time to process. So I wish I had another life or smart in terms of compiler building. Maybe Matthias can comment on that, what he can do. Yeah, maybe please, if you could hand the mic. Matthias or Ivan, they're much more qualified to explain what to do about compile times.
Yeah, so I didn't find the time myself to dive that deep, but yeah, I've seen especially the template code being so bad, because if you have so many template parameters and then nested template parameters, that on my 4K screen I only see one type printed on the whole screen. That cannot be fast, that cannot be memory efficient. And of course, if you have all these strings in main memory, that just kills your cache performance. And nowadays, it's not just only big O notation, right? Sometimes if you're just exceeding your caches, that is sometimes more important to avoid rather than a more efficient algorithm. So all these trade-offs, I think there is a lot of potential to go faster, but it's not necessarily on the side of GNU Radio to solve that. It might be on the side of GCC and potentially also LLVM. I don't know how much they leave lying around in terms of compile time performance there. But again, I would love to go deeper there. I haven't even been able to write a good bug report yet. That would be the first step to do something about it, right? Because typically these things come up with a huge translation unit, and if you want to go to a compiler vendor and say, well, there is a problem, please fix it, you rather want to go with, like, this is a small example that exhibits the problem. Yeah. Any more to add?
Jean-Michel, you wanted to say something? So if there are no more questions, maybe it's a good point for
There's a hand also there.
Thank you, Ralph. I just had a comment on a question on one of your slides. You showed as a non-developer, as a user question, you showed the difference between single processing and a block processing. So for us non-developers, how exactly does this matter in terms of in an experimental scenario, you have some blocks that you need to process sample by sample, like scaling, that would be quite fine. But if you have a kind of a digital filtering, or you have some block of data, so if you're interested in a time-resolved Fourier analysis, that means you need to gather a couple of frames of data before you can make a sensible, take a sensible information out of this. So in this respect, in this ambivalence, what is the way to go, or how should one really think about implementing such things? Thank you.
Yeah, there's several ways how to skin a cat. I mean, like you can. Oh, sorry, I shouldn't have said like. I love cats. There's several ways how to do this. I mean, you can use the process 1 and then just keep a local copy of your history that you need for doing time-resolved information. Let's say if you need to do an FFT of 1024. You take 1024 and then process it, like for an FIR filter, that would work. But that's also one of the reasons why this process bulk way. So like, please, whenever you invoke me only once you have 1024 samples available, and then I produce one sample or one spectrum as an output. So that's very flexible. So if you say like in terms of blocks, they're functions. There can be single sample in, single sample out. There can be erase of data in, erase of data out, erase in, sample out, whatever combinations you need. They're just like these two signatures, either process 1 or process bulk. The process 1 is the simpler one, which can't do decimation, but basically with process bulk, all possible mathematical operations, or nearly all, are possible. There was a limitation before, but maybe this is not a limitation with GR4. What type of data you have in or out. You can even transmit tensors. So if you want to do like a laser calculation of a laser resonator, you could do it with that as well. Also, you could use it for maybe as a SPICE replacement. I mean, like, we haven't looked into that, but you could also maybe, if you're up to it, just try for the fun of it, make a SPICE circuit simulator with GNU radio. If there are no more questions, I mean, like, I'm the last thing standing between you and your well-deserved coffee break. But I think now we can take it a bit more relaxed. Maybe Jean-Michel.
I just wanted just to clarify in 2 minutes what user tutorials were about, because initially I had a plan which I shared with the organizers, and then I had a video call with Shahab, and he shared with me what would be more interesting maybe for the GSI staff, maybe less familiar with GNU Radio. So my plan is to start with GNU Radio for people who have basically never started it. So the first 5 minutes are getting familiar with the user interface, GNU Radio Companion. So everything I'm working on is GNU Radio 3.10, so the one you have in your Linux distribution nowadays. Then I will discuss the teaching potential of GNU Radio. So I'm teaching at bachelor level. So of course, we all know that we're handling complex numbers. So I'll show you how GNU Radio allows you to address what an imaginary voltage is, what a negative frequency is. Even if you know it, I find it interesting that to show that GNU Radio has a very large teaching potential to get intuitive insight that I believe MATLAB or this proprietary software do not have. I'll quickly go into filter characteristics because Marcus keeps on answering on the chat and the mailing list, why is my GNU Radio so slow? And it's not the GNU Radio that is slow, it's the user that's stupid. So how do you design properly your transition width so that you don't overload your flowchart? And finally, because most of you or many of you are already using Python for post-processing their data, we're going to quickly see how you can introduce your Python code into GNU Radio flowchart. So that's already a bit more advanced, how you write a Python block, and you'll see that in 10 lines you can use your Python post-processing inside for real-time processing GNU Radio. So that's the first 2 times 45 minutes that we have today. And then because I'm pretty much convinced in my daily activity that there are other tools in GNU Radio, including Octave, including Python, including external C, next tutorial will be about sharing data with external tools, 0MQ, XMLRPC, pipes, name FIFO, so seeing how you can interface GNU Radio with your existing tools. So that's the 3 topics I would like to address, and it's kind of a different outline than what you had in the program because yeah, it was a bit adapted to what I was asked to share with you. Thanks.
Good. For the people who are going for the user tutorials, they going to be in the KBW building, so that's if you go to the entrance of GSI, just head down past the parking garage by the big building, and then the rearmost building, ground floor, is the other lecturing hall. So it's easy to find.
And I just forgot for the user tutorial, if you want to play by yourself and not just watch me moving a mouse on the screen, I expect you either to have a virtual box or to have a functional GNU Radio 3.10 running on your computer. No specific installation, just a basic apt-get install GNU Radio.
So, good, let's break. Sorry, I've overdrawn a bit. Maybe let's say still Jean-Michel, if it's okay with you, shall we break for an hour, half an hour still? We still break for half an hour.
Can we move a little bit the end also because we have a social event afterwards? So can we shift everything by 15 minutes? To keep
15.
the duration? So we keep 30 minutes break and then we postpone the end of the tutorial by 15 minutes?
Yeah, it was not the idea.
Good, yeah.
Micro pour le chat.
Ah oui.